Hello there. You're listening to Science Blanket, your quiet space for wonder. I'm so glad you've joined me tonight. Tonight, we are wrapping ourselves in the soft, invisible fabric of time. We often think of time as a ticking clock or a rushing stream, pushing us through our days. But tonight, we're going to view it as a vast, ancient landscape, a quiet dimension that stretches out in all directions, holding every moment that ever was and every moment yet to be. Time is not just a measurement. It is the heartbeat of the universe, pulsing so slowly that we often forget to stop and simply feel it. As we begin, imagine time as a slow-moving river of starlight flowing through a deep, silent forest. There is no hurry here. The seconds are as light as falling leaves, and the hours are as steady as the stones on the riverbed. You don't need to keep track of the minutes or worry about the morning. Just let the rhythm of deep time settle over you like a heavy, velvet cloak. If this blanket of eternity helps you find rest, please consider subscribing to the channel. It helps us keep the lights low and the stories flowing for every sleepy mind in our community. Now, take a deep, grounding breath. Feel the gentle pressure of your blankets and the stillness of the room around you. Soften the corners of your eyes, let your tongue drop away from the roof of your mouth, and allow your heavy limbs to sink deep into the earth. The world is waiting, but time is standing still for you right now. Let's explore the sleepy secrets of time together. Time is treated as a physical dimension in Einstein's theory of relativity, intertwined with space to form space-time. When we think about the universe, we often imagine space as something we can move through, something with width and height and depth. But Einstein showed us that time is not separate from space at all. Instead, they are woven together into a single fabric called space-time. This might sound strange at first, because we experience time so differently from the three dimensions of space we move through every day. We can walk forward or backward, left or right, up or down through space whenever we choose. But time seems to flow in only one direction, carrying us along whether we want to go or not. Yet Einstein's equations reveal that time and space are fundamentally connected, that they bend and curve together around massive objects, that they respond to motion and gravity in ways that link them inseparably. Imagine space-time as a vast ocean, with ripples and currents flowing through it. Every object, every particle, every bit of energy creates waves in this ocean. And we, moving through our lives, are traveling through both space and time simultaneously, following paths through this four-dimensional reality that we can barely perceive in its fullness. In relativity, simultaneity is not absolute. Events that appear simultaneous to one observer may not be for another moving differently. This is one of the most profound and puzzling aspects of Einstein's theory. We tend to think that if two things happen at the same moment, they happen at the same moment for everyone, everywhere. But this simply isn't true. Imagine two friends standing beside a train track. One friend is on the platform, standing still. The other is on a train rushing past at tremendous speed. At the exact moment the moving friend passes the stationary one, two lightning bolts strike the tracks, one far ahead of the train and one far behind it. To the friend on the platform, both lightning strikes appear to happen at exactly the same instant. The light from both reaches their eyes at the same time, and the distances are equal, so they conclude the strikes were simultaneous. But the friend on the train sees something different. Because they're moving toward one lightning strike and away from the other, the light from the strike ahead reaches them before the light from the strike behind. From their perspective, moving through space-time along a different path. The lightning strikes did not happen at the same moment at all. One came first, then the other. And neither observer is wrong. There is no universal now, no cosmic clock that ticks the same for everyone. Simultaneity depends on motion, on your path through space-time. What happens at the same time for you might be separated by seconds or even longer for someone else moving differently through the universe. The faster an object moves, the slower time passes for it compared with a stationary observer, a phenomenon called time dilation. This is perhaps the most famous consequence of Einstein's special relativity. If you could board a spacecraft and accelerate to a significant fraction of the speed of light, something remarkable would happen. Time itself would slow down for you relative to everyone you left behind on Earth. It's not that you would feel any different. Your heartbeat would seem normal. Your watch would tick at its usual pace. But compared to the clocks on Earth, your clock would be running slow. If you traveled fast enough for long enough and then returned home, you might find that while only a year had passed for you, decades had gone by on Earth. Your friends would be older. The world would have changed. Time dilation isn't science fiction or theoretical speculation anymore. It's been measured, tested, and confirmed countless times. Particles in accelerators, moving at nearly the speed of light, last longer before decaying than they would if they were standing still. Atomic clocks flown on airplanes show slight differences from clocks left on the ground. The effect is real, even if it's imperceptibly small at the speeds we normally experience. But it tells us something profound about the nature of time itself. Time is not an unchanging backdrop against which events unfold. Time is flexible, malleable, dependent on motion and speed. The faster you go, the slower your clock ticks relative to the rest of the universe. Time also passes more slowly in stronger gravity, meaning clocks at sea level tick slightly slower than clocks on a mountain. This is another form of time dilation, predicted by Einstein's general relativity. Gravity, according to Einstein, is not just a force pulling objects together. It's a curvature of space-time itself. Massive objects like the Earth bend space-time around them, creating wells and curves in the fabric of reality. And where space-time is curved more strongly, where gravity is stronger, time flows more slowly. The difference is incredibly small for the gravity we experience on Earth, but it's measurable. If you live at sea level, closer to the center of the Earth where gravity is slightly stronger, your clock runs just a tiny bit slower than a clock high on a mountaintop where gravity is fractionally weaker. The person on the mountain is aging ever so slightly faster than the person at sea level. Over a lifetime, the difference amounts to microseconds, far too small to notice. But it's there, a real effect of the way gravity shapes time. Deep in the gravity well near a black hole, time dilation becomes extreme. If you could somehow survive near the edge of a black hole's event horizon and watch the universe beyond, you would see time accelerating. Stars would be born and die in what seemed like moments to you. Civilizations would rise and fall. But for the universe watching you, you would appear frozen, barely moving, your time stretched out by the intense gravitational field. GPS satellites must correct for both effects, gaining about 45 microseconds daily from weaker gravity and losing about 7 from velocity, for a net gain of 38 microseconds. This is where time dilation moves from abstract physics into practical technology. The global positioning system that helps us navigate every day relies on extremely precise timing. GPS satellites orbit high above the Earth, sending signals that include timestamp information. Your GPS receiver picks up signals from multiple satellites and uses the tiny differences in arrival times to calculate your exact position. But here's the problem. Those satellites are experiencing time differently than we are on Earth's surface. They're moving fast, orbiting the planet at about 14,000 kilometers per hour, which causes their clocks to run slower due to velocity-based time dilation. At the same time, they're much farther from Earth's center in a weaker gravitational field, which causes their clocks to run faster due to gravitational time dilation. These two effects work in opposite directions. The velocity effect causes the satellite clocks to lose about 7 microseconds per day. The gravitational effect causes them to gain about 45 microseconds per day. The net result is that satellite clocks run about 38 microseconds fast each day compared to clocks on Earth. That might not sound like much, but light travels about 30 centimeters in a nanosecond. In 38 microseconds, light travels more than 11 kilometers. Without correcting for relativity, GPS would accumulate errors of kilometers per day, making the system completely useless. Engineers have to program the satellites to adjust their clock rates to compensate for these relativistic effects, proof that Einstein's century-old theories are essential to our modern world. Astronaut Scott Kelly aged about 5 milliseconds less than his twin Mark after spending nearly a year aboard the ISS. The Kelly twins provided scientists with a remarkable natural experiment in time dilation. Scott Kelly spent 340 days on the International Space Station while his identical twin brother Mark remained on Earth. During that time, Scott was orbiting Earth at about 28,000 kilometers per hour, fast enough that time dilation effects, though tiny, became measurable. Because Scott was moving so quickly relative to Mark, time passed slightly more slowly for him. When Scott returned to Earth, he had aged about 5 milliseconds less than his twin. 5 milliseconds over 340 days is an almost imperceptibly small difference, but it's real and measurable with precise instruments. It means that Scott experienced fractionally less time than Mark during that year. Of course, the twins looked the same age. The difference is far too small to see or feel. But it demonstrates that time dilation isn't just something that happens to particles in laboratories or clocks on satellites. It happens to people, too. Every astronaut who has ever orbited Earth has returned slightly younger than they would have been if they'd stayed on the ground, though the difference is always vanishingly small at the speeds we can achieve. If we could build spacecraft that traveled at speeds closer to that of light, the effects would become dramatic. Astronauts could travel for what felt like months or years and return to find that decades or centuries had passed on Earth. Time dilation was experimentally confirmed in 1941 when fast-moving muons survived longer than expected. Muons are subatomic particles, similar to electrons but heavier. They're unstable, decaying into other particles with an average lifetime of about 2.2 microseconds when at rest. Cosmic rays constantly bombard Earth's atmosphere from space, creating showers of particles including muons high in the atmosphere. Here's the puzzle that physicists noticed. Even moving at nearly the speed of light, muons created 10 kilometers up in the atmosphere should decay long before reaching the ground. In 2.2 microseconds, even at light speed, they should only travel about 660 meters. And yet muons were being detected at sea level in large numbers. The explanation is time dilation. From our perspective on Earth, the muons are moving so fast that time is passing more slowly for them. Time also passes more slowly in stronger gravity, meaning clocks at sea level tick slightly slower than clocks on a mountain. This is another form of time dilation, predicted by Einstein's general relativity. Gravity, according to Einstein, is not just a force pulling objects together. It's a curvature of space-time itself. Massive objects like the Earth bend space-time around them, creating wells and curves in the fabric of reality. And where space-time is curved more strongly, where gravity is stronger, time flows more slowly. The difference is incredibly small for the gravity we experience on Earth, but it's measurable. If you live at sea level, closer to the center of the Earth where gravity is slightly stronger, your clock runs just a tiny bit slower than a clock high on a mountaintop where gravity is fractionally weaker. The person on the mountain is aging ever so slightly faster than the person at sea level. Over a lifetime, the difference amounts to microseconds, far too small to notice. But it's there, a real effect of the way gravity shapes time. Deep in the gravity well near a black hole, time dilation becomes extreme. If you could somehow survive near the edge of a black hole's event horizon and watch the universe beyond, you would see time accelerating. Stars would be born and die in what seemed like moments to you. Civilizations would rise and fall. But for the universe watching you, you would appear frozen, barely moving, your time stretched out by the intense gravitational field. GPS satellites must correct for both effects, gaining about 45 microseconds daily from weaker gravity and losing about 7 from velocity, for a net gain of 38 microseconds. This is where time dilation moves from abstract physics into practical technology. The global positioning system that helps us navigate every day relies on extremely precise timing. GPS satellites orbit high above the Earth, sending signals that include timestamp information. Your GPS receiver picks up signals from multiple satellites and uses the tiny differences in arrival times to calculate your exact position. But here's the problem. Those satellites are experiencing time differently than we are on Earth's surface. They're moving fast, orbiting the planet at about 14,000 kilometers per hour, which causes their clocks to run slower due to velocity-based time dilation. At the same time, they're much farther from Earth's center in a weaker gravitational field, which causes their clocks to run faster due to gravitational time dilation. These two effects work in opposite directions. The velocity effect causes the satellite clocks to lose about 7 microseconds per day. The gravitational effect causes them to gain about 45 microseconds per day. The net result is that satellite clocks run about 38 microseconds fast each day compared to clocks on Earth. That might not sound like much, but light travels about 30 centimeters in a nanosecond. In 38 microseconds, light travels more than 11 kilometers. Without correcting for relativity, GPS would accumulate errors of kilometers per day, making the system completely useless. Engineers have to program the satellites to adjust their clock rates to compensate for these relativistic effects, proof that Einstein's century-old theories are essential to our modern world. Astronaut Scott Kelly aged about 5 milliseconds less than his twin Mark after spending nearly a year aboard the ISS. The Kelly twins provided scientists with a remarkable natural experiment in time dilation. Scott Kelly spent 340 days on the International Space Station while his identical twin brother Mark remained on Earth. During that time, Scott was orbiting Earth at about 28,000 kilometers per hour, fast enough that time dilation effects, though tiny, became measurable. Because Scott was moving so quickly relative to Mark, time passed slightly more slowly for him. When Scott returned to Earth, he had aged about 5 milliseconds less than his twin. 5 milliseconds over 340 days is an almost imperceptibly small difference, but it's real and measurable with precise instruments. It means that Scott experienced fractionally less time than Mark during that year. Of course, the twins looked the same age. The difference is far too small to see or feel. But it demonstrates that time dilation isn't just something that happens to particles in laboratories or clocks on satellites. It happens to people, too. Every astronaut who has ever orbited Earth has returned slightly younger than they would have been if they'd stayed on the ground, though the difference is always vanishingly small at the speeds we can achieve. If we could build spacecraft that traveled at speeds closer to that of light, the effects would become dramatic. Astronauts could travel for what felt like months or years and return to find that decades or centuries had passed on Earth. Time dilation was experimentally confirmed in 1941 when fast-moving muons survived longer than expected. Muons are subatomic particles, similar to electrons but heavier. They're unstable, decaying into other particles with an average lifetime of about 2.2 microseconds when at rest. Cosmic rays constantly bombard Earth's atmosphere from space, creating showers of particles including muons high in the atmosphere. Here's the puzzle that physicists noticed. Even moving at nearly the speed of light, muons created 10 kilometers up in the atmosphere should decay long before reaching the ground. In 2.2 microseconds, even at light speed, they should only travel about 660 meters. And yet muons were being detected at sea level in large numbers. The explanation is time dilation. From our perspective on Earth, the muons are moving so fast that time is passing more slowly for them. The universe is about 13.8 billion years old, containing all cosmic history from galaxy formation to life on Earth. When we look up at the night sky, we're looking back through time. The light from distant stars has traveled for years, sometimes centuries or millennia, to reach our eyes. The farther we look into space, the farther back in time we see. And when astronomers peer through their most powerful telescopes, examining the faintest, most distant galaxies, they're seeing light that has been traveling toward us for billions of years. Light that left its source when the universe was young. By studying this ancient light, by measuring the cosmic microwave background radiation that fills all of space, by observing how galaxies move and how the universe expands, scientists have determined that our universe began approximately 13.8 billion years ago. Everything that exists, all the matter and energy, all the space itself, emerged from an incredibly hot, incredibly dense state in an event we call the Big Bang. In those first moments, the universe was too hot for atoms to exist. Only after hundreds of thousands of years of expansion and cooling could the first hydrogen atoms form. Gravity slowly pulled this primordial gas into clumps that became the first stars, and those stars gathered into the first galaxies. Over billions of years, stars have been born and died, some exploding as supernovae and scattering heavier elements into space. Those elements became the building blocks of planets, and on at least one of those planets, orbiting an ordinary star in an ordinary galaxy, life emerged. All of Earth's history, from the formation of our world 4.5 billion years ago to the evolution of single-celled organisms, to the age of dinosaurs, to the brief moment of human civilization, all of it fits within that vast cosmic timeline of 13.8 billion years. The universe's expansion rate remains disputed, producing the unresolved Hubble tension. Edwin Hubble discovered in the 1920s that the universe is expanding, that galaxies are moving away from us, and that the farther away a galaxy is, the faster it appears to be receding. This discovery revolutionized our understanding of the cosmos and led to the Big Bang theory. Scientists have been working ever since to measure exactly how fast the universe is expanding, a number called the Hubble constant. But here's the puzzle that has emerged in recent years. When astronomers measure the expansion rate by looking at nearby galaxies and using certain types of stars as distance markers, they get one answer. When they measure it by looking at the cosmic microwave background, the afterglow of the Big Bang itself, and using our best theoretical models of the early universe, they get a different answer. The difference isn't huge, but it's persistent and statistically significant. It's known as the Hubble tension, and it's one of the most important unsolved problems in cosmology today. Either there's some subtle error in one of the measurement methods that no one has identified yet, or something is genuinely wrong with our understanding of how the universe works. Perhaps there's some unknown property of dark energy, the mysterious force driving the universe's accelerating expansion. Perhaps our models of the early universe need revision. Perhaps there's new physics we haven't discovered yet. The Hubble tension reminds us that even with all our sophisticated instruments and elegant theories, the universe still holds surprises, still presents us with puzzles that challenge our understanding. The horizon problem questions how distant regions of space appear uniform despite limited interaction time. When we look at the cosmic microwave background, that faint glow of radiation left over from the early universe, we see something remarkable. The temperature is almost perfectly uniform in every direction. No matter where we look in the sky, the temperature of this ancient light is the same to within a tiny fraction of a degree. This uniformity tells us that the early universe was remarkably smooth and homogeneous. But there's a problem. According to our calculations, regions of space that are on opposite sides of the observable universe have never been in contact with each other. They are so far apart that even light, traveling since the beginning of time, hasn't had enough time to pass between them. If they've never been in contact, never exchanged energy or information, how did they end up at exactly the same temperature? It's as if you found 2 cups of coffee on opposite sides of the world that had never interacted with each other, yet they were at precisely the same temperature. The most widely accepted solution to this horizon problem is cosmic inflation, a theory proposing that in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light. Space itself was stretching, and during this brief period of inflation, regions that would later be far apart were once close enough to reach thermal equilibrium. Then inflation carried them apart, preserving that uniformity. Inflation solves the horizon problem elegantly, but it raises other questions and remains an active area of research and debate. The block universe theory suggests past, present, and future coexist equally, making now a subjective illusion. This is one of the most philosophically challenging ideas to emerge from relativity. We experience time as a flow, as a river carrying us from past through present toward future. The past seems gone, existing only in memory. The future seems unreal, not yet arrived. Only the present moment feels truly real. But the equations of relativity suggest something different. They suggest that space-time is a 4-dimensional structure in which past, present, and future all exist equally. Imagine space-time as a complete object, a block containing all of history and all of the future. Your entire life, from birth to death, exists as a 4-dimensional path through this block. The sensation of now, The feeling that one particular moment is special and present is simply an artifact of consciousness, a subjective experience rather than a fundamental property of reality. According to the block universe view, all moments are equally real. The moment you were born still exists. The moment you're experiencing right now exists. And the moment of your death already exists as well, waiting in what we perceive as the future. You're simply moving along your path through space-time, your consciousness illuminating different moments in sequence, creating the illusion of time's flow. This view eliminates any fundamental difference between past, present, and future. It suggests that the entire history of the universe, from the Big Bang to whatever ending awaits, exists as a single, timeless structure. It's a strange and difficult idea, one that challenges our deepest intuitions about the nature of time and existence. Entropy's arrow of time dictates why time flows forward rather than backward. Most of the laws of physics are time reversible. If you watched a film of two billiard balls colliding and someone ran the film backward, the backward version would look just as physically plausible as the forward version. The fundamental equations governing how particles interact work equally well whether time runs forward or backward. And yet we never see broken eggs reassemble themselves or heat flowing spontaneously from cold objects to hot ones. Time clearly has a direction. Things age, decay, break down. The universe seems to have an arrow pointing from past to future. The explanation lies in the second law of thermodynamics, which states that entropy, a measure of disorder or randomness, always increases in a closed system. Imagine a pristine room, everything organized and in its place. Over time, without effort, the room becomes messier. Papers scatter, dust accumulates, objects get misplaced. It takes energy and effort to organize the room again. Disorder naturally increases. This is entropy in action. At the beginning of the universe, for reasons we don't fully understand, entropy was very low. Everything was in a highly organized, low-entropy state. Since then, entropy has been increasing, will continue increasing, and this increase gives time its direction. The past is the direction of lower entropy, the future is the direction of higher entropy. We remember the past but not the future because memory formation is an entropy-increasing process. Causes precede effects because causal chains follow the entropy gradient. The arrow of time emerges from thermodynamics, from the statistical behavior of countless particles all moving from order toward disorder. Supertask paradoxes, like Thomson's lamp, challenge whether infinite actions can occur in finite time. Imagine a lamp with a switch. You turn it on. After 1 minute, you turn it off. After another 30 seconds, you turn it on again. After another 15 seconds, off. Then on after 7.5 seconds. You continue this pattern, each switch happening in half the time of the previous one. After 2 minutes total, you will have flipped the switch infinitely many times. The question is this: at the end of 2 minutes, is the lamp on or off? This is Thomson's lamp paradox, named after philosopher James Thomson. It seems like a simple question, but it has no answer. If the lamp is on, then there must have been a last switch that turned it on. But there is no last switch in an infinite sequence. The same problem occurs if we say it's off. We can't say it's in some indeterminate state because the lamp is either on or off at any given moment. Thomson's lamp is an example of a supertask, a scenario involving infinitely many actions completed in finite time. These paradoxes suggest that while mathematics allows us to work with infinity, physical reality might not. Perhaps space-time is quantized, broken into discrete units, making true infinity impossible. Perhaps supertasks reveal limitations in our concepts rather than genuine possibilities. They sit at the boundary between mathematics, physics, and philosophy, challenging us to think carefully about what infinity means and whether the physically possible is the same as the mathematically describable. Zeno's paradoxes argue motion is impossible due to infinite divisions of time and space. More than 2,000 years ago, the ancient Greek philosopher Zeno of Elea proposed a series of paradoxes meant to show that motion is impossible. The most famous is the paradox of Achilles and the tortoise. Imagine Achilles, a swift runner, racing against a tortoise. Achilles gives the tortoise a head start. Before Achilles can overtake the tortoise, he must first reach the point where the tortoise started. But by the time Achilles reaches that point, the tortoise has moved a bit farther. So Achilles must reach this new point. But by the time he does, the tortoise has moved again. No matter how many times Achilles reaches where the tortoise was, the tortoise has always moved a bit farther ahead. According to Zeno's logic, Achilles must complete infinitely many tasks to catch the tortoise, and completing infinitely many tasks is impossible. Therefore, Achilles can never overtake the tortoise. Of course, we know from experience that faster runners do overtake slower ones. Zeno's paradoxes don't reflect reality, but they do raise deep questions about the nature of space, time, and infinity. The modern resolution involves understanding that an infinite series can sum to a finite value. The infinite number of intervals Achilles must traverse add up to a finite distance, which he covers in finite time. Calculus, developed in the 17th century, gave us the mathematical tools to handle these infinite sums precisely. But Zeno's paradoxes still provoke thought about whether space and time are infinitely divisible or whether there's some smallest unit beyond which further division is meaningless. Quantum time crystals, discovered in 2016, repeat motion without energy input, defying classical expectations. In the landscape of strange quantum phenomena, time crystals stand out as particularly counterintuitive. Ordinary crystals have structures that repeat in space. Salt crystals, for example, have atoms arranged in regular, repeating patterns extending in 3 dimensions. A time crystal is something different. It's a system that repeats in time rather than space, oscillating in a regular pattern without consuming energy. This seems to violate basic principles. Normally, periodic motion requires energy input. A pendulum swinging back and forth gradually loses energy to friction and air resistance until it stops. To keep it swinging, you must add energy. But time crystals, predicted theoretically in 2012 and first created experimentally in 2016, exhibit perpetual motion without energy loss. They exist in their quantum ground state, the lowest energy configuration, yet they still change periodically over time. They're not violating the laws of thermodynamics, but they are behaving in ways that classical physics would forbid. Time crystals exist only because of quantum mechanics, because of the strange rules governing the atomic and subatomic world. They're created in carefully controlled laboratory conditions, often using trapped ions or other quantum systems. They represent a new phase of matter, distinct from solids, liquids, gases, and other known phases. Time crystals are still poorly understood, and scientists are still exploring their properties and potential applications. They might someday be useful for quantum computing or other technologies. For now, they stand as yet another reminder that the quantum world operates according to rules that defy our everyday intuitions. The Planck time, about 5.39 times 10 to the negative 44 seconds, represents the smallest meaningful unit in physics. We've seen how time can be divided into smaller and smaller intervals. A second can be divided into milliseconds, then microseconds, then nanoseconds, and so on. But physics suggests there may be a limit to this division, a fundamental timescale below which our current theories break down. This is the Planck time, named after physicist Max Planck. It's derived from fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. The Planck time is astonishingly brief. Written out, it's about 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 seconds have occurred in the entire 13.8 billion year history of the universe. At timescales this small, quantum effects and gravitational effects become equally important, and our current theories of physics, quantum mechanics, and general relativity cannot be reconciled. To understand what happens at the Planck time, we would need a theory of quantum gravity, a unified framework that we don't yet possess. Below the Planck time, the very concepts of space and time might break down or become meaningless. Some theories suggest space-time itself is quantized, made of discrete units rather than being infinitely divisible. The Planck time might represent the smallest tick of the universe's clock, the fundamental temporal resolution of reality. Even smaller units like attoseconds, yoctoseconds, and rontoseconds now probe electron motion and particle decay. While the Planck time represents a theoretical limit, scientists have developed the ability to measure and manipulate extraordinarily brief time intervals far shorter than we encounter in everyday life. An attosecond is 1/quintillionth of a second, a billion times shorter than a nanosecond. Attosecond physics, developed over the past few decades, allows scientists to observe electrons moving within atoms. Electrons orbit atomic nuclei incredibly quickly, and attosecond lasers can effectively freeze this motion, allowing us to see quantum processes unfold in time. A yoctosecond is even shorter, 1/septillionth of a second. This is approaching the time scale of interactions within atomic nuclei. And recently, physicists have begun working with rontoseconds, also called quectoseconds, which are 1/octillionth of a second. At this scale, we're measuring the time it takes for light to cross a proton. These measurements help us understand the fundamental processes governing particle physics and quantum mechanics. They represent the cutting edge of our ability to probe the nature of time itself. Each new order of magnitude we reach in time measurement opens new windows into the universe's workings, revealing processes and phenomena that occur at timescales previously beyond our reach. As we develop better tools and more refined techniques, we push the boundaries of temporal resolution, exploring the universe's fastest processes and deepest mysteries, all while the vast majority of us drift through time at the gentle pace of seconds and minutes and hours, unaware of the frenetic quantum dance occurring at every moment in the atoms that make up our world. Earth's rotation is gradually slowing due to tidal interactions with the Moon. Our planet spins on its axis, giving us day and night, but this rotation is not constant. It's changing, imperceptibly slowly from our human perspective, but measurably over long periods of time. The Moon is responsible for this gradual deceleration. As the Moon orbits Earth, its gravity pulls on our planet, creating the tides we see in the oceans. Water rises and falls along coastlines twice each day as Earth rotates beneath these tidal bulges. But this process isn't perfectly efficient. The friction between moving water and the ocean floor, between tides and coastlines, dissipates energy. This energy has to come from somewhere, and it comes from Earth's rotation. The same tidal forces also affect Earth's crust, creating slight bulges even in solid rock, though these are much smaller than ocean tides. Over time, all this friction acts like a brake on Earth's spin. The effect is tiny from moment to moment, but it accumulates. Earth is spinning down, gradually losing rotational energy, and as it does, our days grow longer. At the same time, the Moon is slowly drifting away from Earth, receding at about 3.8 centimeters per year. The angular momentum lost by Earth's rotation is transferred to the Moon's orbit, causing it to spiral gradually outward. This is a beautiful example of conservation of angular momentum, one of the fundamental principles of physics. The Earth-Moon system as a whole maintains its total angular momentum, but the distribution shifts over time, slowing Earth's spin and pushing the Moon farther away. As a result, days lengthen by about 1.7 milliseconds per century. The rate at which Earth's rotation slows is remarkably consistent over long time scales. Each century, the length of a day increases by roughly 1.7 milliseconds. That's an almost unimaginably small change. In a human lifetime, days get longer by perhaps a few hundredths of a millisecond, far too small to notice. Even sophisticated timekeeping would struggle to detect the change over just a few decades. But over centuries and millennia, these tiny increments add up. 1,000 years from now, days will be about 17 milliseconds longer than they are today. 10,000 years from now, days will be nearly a fifth of a second longer. The rate isn't perfectly constant because other factors can affect Earth's rotation as well. Large earthquakes can redistribute mass in Earth's crust, momentarily changing the planet's moment of inertia and slightly altering rotation speed, like a figure skater pulling their arms in to spin faster or extending them to slow down. The melting of glacial ice, the filling of reservoirs, even large-scale weather patterns can cause tiny variations in the length of a day. But averaged over long periods, the tidal braking dominates, and the 1.7 milliseconds per century figure gives us a good estimate of the long-term trend. Scientists can verify this rate by studying ancient astronomical records, looking at descriptions of eclipses from centuries or millennia ago and calculating where the Moon should have been in the sky based on current orbital parameters, then comparing that to where historical observers actually saw it. Hundreds of millions of years ago, a day lasted only 22 to 23 hours. If we could travel back in time to the age of the dinosaurs, about 70 million years ago, we would find that a day was only about 23.5 hours long. The difference of half an hour might not seem dramatic, but it would mean the Earth was spinning noticeably faster. Go back further, to 350 million years ago when the first forests were spreading across the continents and the first amphibians were venturing onto land, and a day lasted only about 22 hours. A year still had roughly the same duration, because Earth's orbit around the Sun hasn't changed significantly. But that year contained more days, perhaps 400 of them instead of 365. We know this from multiple lines of evidence. Some corals and other marine organisms lay down daily growth rings, similar to tree rings but on a much finer scale. By studying fossil corals from different geological periods, paleontologists can count the growth rings in annual bands and determine how many days were in a year when those corals were alive. Ancient tidal patterns preserved in sedimentary rocks also provide evidence about Earth's rotation rate in the distant past. These studies consistently show that days were shorter long ago. If we could go back even further, to Earth's earliest history billions of years ago, we would find days that were only a few hours long. The moon was much closer then, and tidal forces were much stronger, breaking Earth's rotation more rapidly. Over the vast sweep of geological time, Earth's spin has gradually slowed, days have lengthened, and the moon has retreated into a more distant orbit. A solar day differs from Earth's true rotation period, the sidereal day, by about 4 minutes. When we talk about a day, we usually mean a solar day, the time from one noon to the next, or the time it takes for the sun to return to the same position in the sky. This is 24 hours, by definition, since we've constructed our clocks and our concept of time around the solar day. But Earth's true rotation period is slightly different. If instead of watching the sun, we watched a distant star, we would find that the star returns to the same position in the sky in slightly less than 24 hours. This is called a sidereal day, from the Latin word for star. A sidereal day is about 23 hours, 56 minutes, and 4 seconds. The difference arises because Earth is orbiting the Sun while it rotates. Imagine Earth at some point in its orbit, rotating once on its axis. After this rotation, Earth has also moved a bit along its orbit. To bring the Sun back to the same position in the sky, Earth needs to rotate a little bit more, about 1 extra degree, to compensate for its orbital motion. This extra rotation takes about 4 minutes. The stars are so distant that Earth's orbital motion doesn't change their apparent position significantly, so a sidereal day represents Earth's true rotation period relative to the fixed background of space. Astronomers use sidereal time when pointing telescopes because it tells them where objects in the sky will be based on Earth's actual rotation. But for daily life, we use solar time, because our activities are synchronized with the Sun, not with the distant stars. Earth's core rotates slightly faster than the surface, completing an extra spin every 400 years. Deep beneath our feet, beneath the crust and mantle, lies Earth's core, a sphere of iron and nickel about the size of the moon. The outer core is liquid, a churning sea of molten metal. The inner core is solid, crystallized under the immense pressure of the overlying layers. And this inner core doesn't rotate in perfect lockstep with the rest of the planet. Studies using seismic waves, vibrations that travel through Earth after earthquakes, have revealed that the inner core rotates slightly faster than the mantle and crust. The difference is small, about 1/10 to 1 degree per year faster, which means the inner core completes 1 extra rotation relative to the surface roughly every 400 years or so. The mechanism driving this superrotation isn't fully understood, but it likely involves electromagnetic coupling between the inner core and the liquid outer core, where Earth's magnetic field is generated. The motion of conducting fluid in the outer core creates the magnetic field, and this field in turn exerts forces on the solid inner core, potentially causing it to rotate at a different rate. Some studies have suggested that the inner core's rotation rate varies over time, sometimes speeding up and sometimes slowing down relative to the surface. There's even evidence that the inner core might occasionally reverse its relative rotation direction. These findings are based on subtle changes in the travel times of seismic waves passing through the core, and they're challenging to interpret. Earth's deep interior remains one of the most inaccessible and mysterious parts of our planet, a hidden realm where processes unfold over decades and centuries that we're only beginning to understand. Earth's atmosphere superrotates, circling the planet every 3 to 4 days. While Earth's solid surface takes 24 hours to complete one rotation, the atmosphere doesn't simply move along with the surface. In certain regions, particularly in the upper atmosphere and near the poles, winds race around the planet much faster than the surface below them rotates. This phenomenon is called superrotation. It's most dramatic on other planets like Venus, where the atmosphere circles the planet in just 4 days, even though the solid planet takes 243 days to rotate once. But Earth exhibits superrotation too, especially in the stratosphere at tropical latitudes. Winds in the upper atmosphere can complete a circuit around Earth in just a few days, moving much faster than the rotation of the surface beneath them. These winds are driven by complex interactions between solar heating, Earth's rotation, and atmospheric dynamics. Near the equator, where the sun's heating is strongest, air rises, creating circulation patterns. The Coriolis effect, caused by Earth's rotation, deflects these moving air masses, creating the trade winds and prevailing westerlies that mariners have relied on for centuries. In the upper atmosphere, these patterns create jets and currents that can achieve remarkable speeds. Understanding atmospheric superrotation is important for weather prediction and climate modeling. It affects how heat is distributed around the planet, how storms develop and move, and how energy flows through the climate system. Every breath we take is part of this vast, dynamic system, this ocean of air that swirls around our rotating planet in patterns far more complex than simple co-rotation. Jet streams can encircle Earth in under a week at speeds exceeding 200 miles per hour. High in the atmosphere, typically between 20,000 and 40,000 feet, narrow bands of extremely fast-moving air flow around the planet. These are the jet streams, rivers of wind that can reach speeds of 200, 250, even occasionally 300 miles per hour during winter months when temperature contrasts are strongest. There are several major jet streams, including the polar jet stream that flows at high latitudes and the subtropical jet stream closer to the equator. They meander and shift, sometimes splitting into multiple branches, sometimes merging together. Their positions and strengths vary with the seasons and influence weather patterns dramatically. The jet streams form at boundaries between air masses of very different temperatures. Cold polar air meets warmer air from lower latitudes, and the temperature difference drives powerful winds. Because of Earth's rotation and the Coriolis effect, these winds flow predominantly from west to east. At their peak speeds, jet streams can circle the entire Earth in less than a week. A parcel of air caught in a strong jet stream might travel from North America across the Atlantic to Europe in less than a day. Airlines take advantage of jet streams, planning routes that ride these high-altitude winds when flying eastward, cutting hours off flight times and saving fuel. Westbound flights avoid the jet stream when possible, as fighting against such powerful headwinds would waste time and fuel. Pilots and meteorologists constantly monitor jet stream positions and strengths, because these atmospheric rivers play a crucial role in steering weather systems, determining where storms will develop and which regions will experience clear skies or precipitation. Ancient structures like Stonehenge tracked solstices over 5,000 years ago. Long before modern astronomy, before telescopes and mathematical models of planetary motion, ancient peoples were carefully observing the sky and marking the passage of time. Stonehenge, the famous stone circle on England's Salisbury Plain, was constructed in stages over many centuries, with a major stone circle erected around 2500 BCE. The monument's alignment is striking and deliberate. On the summer solstice, the longest day of the year, the sun rises directly over the heel stone when viewed from the center of the circle. On the winter solstice, the shortest day, the setting sun aligns with the central stone structures. These alignments are too precise to be coincidental. The builders of Stonehenge, working with nothing but their observations of the sky and careful surveying, created a structure that marks the turning points of the year. We don't know exactly what rituals or ceremonies took place at Stonehenge, but the astronomical alignment suggests the site had deep significance related to the cycles of the sun and seasons. Stonehenge is just one of many megalithic structures from this period. Across Europe and the Mediterranean, ancient peoples were building stone circles, burial mounds, and temples with astronomical orientations. These monuments required immense effort, sometimes involving the transport of massive stones over long distances. That people invested such resources in creating astronomical markers tells us something important about how ancient cultures understood time, how they related to the cosmos, and how they organized their societies around celestial cycles. Göbekli Tepe aligned stone pillars to stellar risings around 9600 BCE. In southeastern Turkey, on a hilltop overlooking the plains, lies what may be the world's oldest known temple complex. Göbekli Tepe dates to approximately 9600 BCE, making it more than 11,000 years old, older than Stonehenge by over 6,000 years, older even than agriculture and settled civilization in the region. The site consists of several circular and oval structures formed by massive T-shaped limestone pillars, some weighing up to 20 tons, carved and erected by people who were still hunter-gatherers, living before the development of farming, before the invention of pottery or metal tools. The pillars are arranged in circles and decorated with elaborate carvings of animals: foxes, lions, scorpions, snakes, birds, and strange human-like figures. Recent research suggests that the arrangement of the pillars and structures at Göbekli Tepe incorporated astronomical alignments. Certain pillars may have been positioned to mark the rising points of bright stars or constellations as they appeared on the horizon at specific times of year. The builders of Göbekli Tepe were tracking celestial events, encoding their observations in stone. This pushes back the timeline of astronomical observation and monument building by thousands of years. It reveals that even hunter-gatherer societies, long before the rise of agriculture and cities, were paying careful attention to the sky, noting the movements of celestial bodies, and incorporating that knowledge into their sacred architecture. Göbekli Tepe challenges our assumptions about when human societies began systematically observing and recording astronomical phenomena. A lunar calendar carved in Scotland around 1800 BCE tracked moon phases with remarkable precision. At a site called Warren Field in Scotland, archaeologists discovered something extraordinary: a series of pits carefully dug and aligned in an arc that appears to represent a lunar calendar. The pits date to approximately 8000 BCE, making this the oldest known calendar in the world, even older than Göbekli Tepe. The arrangement of 12 pits, each representing a lunar month, tracks the phases of the moon through the year. But there's more sophistication here than simply counting moons. A lunar year, consisting of 12 lunar months, is about 11 days shorter than a solar year. Without correction, a purely lunar calendar drifts out of sync with the seasons. The people who created the Warren Field calendar seem to have understood this problem and incorporated a solution. The alignment of the pits with a landscape feature, A notch in the distant hills where the midwinter sun rises allowed them to periodically recalibrate their lunar calendar to the solar year. This required careful, sustained observation over years or decades to understand the relationship between lunar and solar cycles, and then the planning and effort to create a monument encoding that understanding. The Warren Field calendar is a testament to the sophistication of Mesolithic peoples, those who lived in the period after the Ice Age but before the development of agriculture. These were not simple hunter-gatherers struggling merely to survive. They were people who observed the sky, understood complex cyclical patterns, and created lasting markers to track time, to coordinate activities, to connect with the rhythms of the cosmos that governed their world. Before time zones, towns kept local solar time, which became chaotic with railways. For most of human history, time was a local affair. Each town, each village, each city kept its own time based on the position of the sun in the sky. When the sun reached its highest point, crossing the meridian directly overhead, that was noon. This system worked perfectly well when travel was slow and communities were relatively isolated. If the neighboring town's clocks showed a different time than yours, it didn't matter much because you rarely needed to coordinate activities with them. But the Industrial Revolution changed everything. Suddenly, people and goods were moving rapidly across long distances on railways. Trains needed schedules, and schedules required a common understanding of time. But there was no common time. In Britain alone, different cities kept different local times. London time might differ from Bristol time by 10 or 15 minutes. A train leaving London at noon London time would arrive in Bristol when Bristol's clocks showed something different. Railway companies initially tried to solve this problem by running on their own time, ignoring local times entirely. Stations would have multiple clocks showing both railway time and local time. The confusion was enormous. Travelers constantly struggled to determine when trains would actually depart. Was that schedule printed in local time or railway time? The situation was even more chaotic in North America, where vast distances and numerous railway companies created a bewildering patchwork of conflicting times. Some cities had multiple competing time standards. The need for a better system became urgent as rail networks expanded and the pace of travel and commerce accelerated. Sanford Fleming proposed global time zones in 1879 after missing a train. The man who would solve this temporal chaos was a Scottish-Canadian engineer and inventor named Sanford Fleming. In 1876, Fleming missed a train in Ireland because a printed schedule listed the time incorrectly. Using PM instead of AM, frustrated by this experience and aware of the broader problems with timekeeping, Fleming began developing a solution. By 1879, he had proposed a comprehensive system of global time zones. Fleming's idea was elegant in its simplicity. He suggested dividing the world into 24 zones, each spanning 15 degrees of longitude, corresponding to the 24 hours in a day. Within each zone, all clocks would show the same time. Moving from one zone to the next would change the time by exactly 1 hour. Fleming also proposed a prime meridian that would serve as the reference point for this system, though he suggested it should pass through a neutral location rather than any major city to avoid national rivalry. He initially advocated for a decimal time system as well, dividing the day into more regular units, though this part of his proposal was never adopted. Fleming spent years promoting his time zone system, writing papers, giving lectures, and corresponding with scientists and officials around the world. He recognized that standardizing time was not just a technical problem but also a political and diplomatic one. Countries would need to agree on where zones would be drawn and which meridian would serve as the prime meridian. Fleming's persistence and the undeniable practical benefits of his system eventually led to its adoption, though the process took years and required international cooperation. The International Meridian Conference of 1884 standardized Greenwich as the prime meridian. In October 1884, delegates from 25 nations gathered in Washington, D.C. for the International Meridian Conference. The purpose was to establish a common prime meridian that would serve as the 0 point for longitude and for the newly proposed time zone system. Several meridians were in use at the time. Many maps used the meridian passing through Paris as their reference. Others used Washington, Cadiz, or other cities. This multiplicity of standards created confusion in navigation and cartography. The conference debated which meridian to adopt. The Greenwich Meridian, passing through the Royal Observatory in Greenwich, England, had practical advantages. It was already widely used by mariners, appearing on many nautical charts and serving as the reference for the British Admiralty's Naval Almanac. Roughly 2/3 of all shipping tonnage already used Greenwich-based charts. But there was resistance to adopting a meridian that passed through a major colonial power. France, in particular, objected and abstained from the final vote. After days of discussion, the conference voted to adopt the Greenwich Meridian as the international prime meridian. They also recommended dividing the world into time zones based on this meridian, with a universal day beginning at midnight at Greenwich. It would take years for all countries to implement these standards. France, for instance, continued using Paris time officially until 1911, though it did adopt time zones offset from Greenwich. But the 1884 conference marked the beginning of our modern system of global timekeeping, creating a framework that would enable the increasingly interconnected world of the 20th century. Coordinated universal time became the global reference standard. As timekeeping became more precise in the mid-20th century, the old system of Greenwich Mean Time, based on the Earth's rotation, began to show limitations. Advances in atomic clocks revealed that Earth's rotation is not perfectly uniform. It varies slightly due to tidal forces, atmospheric effects, and other factors. A new time standard was needed that would be both extremely precise and practical for everyday use. In 1960, the International Radio Consultative Committee introduced Coordinated Universal Time, abbreviated UTC. The abbreviation doesn't match the English name because it represents a compromise between the English Coordinated Universal Time and the French Temps Universal Coudon. UTC is based on International Atomic Time, an extremely precise timescale maintained by a network of atomic clocks around the world. But because human activities and natural phenomena are tied to Earth's rotation, UTC is also kept close to solar time. This is accomplished through the occasional insertion of leap seconds, which we'll discuss in a moment. UTC serves as the reference for civil timekeeping worldwide. When we talk about time zones, they're defined as offsets from UTC. A location at UTC +5 has clocks set 5 hours ahead of UTC. When it's noon Universal Time Coordinated, it's 5 p.m. in that time zone. UTC replaced Greenwich Mean Time as the international standard, though in practice, for most purposes, the two are nearly identical. UTC provides the world with a common temporal reference point, enabling everything from international communications and financial transactions to the synchronization of computer networks and GPS satellites. Leap seconds are occasionally added to align atomic time with Earth's irregular rotation. Atomic clocks keep time with extraordinary precision, based on the unchanging vibrations of atoms. But Earth's rotation, as we discussed earlier, is gradually slowing. It's also subject to small, irregular variations. Over time, a discrepancy develops between atomic time, which ticks along with perfect regularity, and solar time, which is based on Earth's actual rotation. To prevent these two timescales from drifting too far apart, leap seconds are occasionally inserted into UTC. A leap second is literally an extra second added to a day, usually at the end of June or December. When a leap second is added, clocks count from 23 hours 59 minutes and 59 seconds to 23 hours 59 minutes and 60 seconds to midnight, instead of jumping directly from 23 hours 59 minutes and 59 seconds to midnight. This keeps UTC within 0.9 seconds of solar time. The decision to add a leap second is made by the International Earth Rotation and Reference System Service, which monitors Earth's rotation rate. Since the first leap second in 1972, about 27 have been added, though the rate is irregular because Earth's rotation doesn't slow at a perfectly constant rate. Leap seconds can cause problems for computer systems that aren't programmed to handle them. In our interconnected digital world, where precise timing is crucial for everything from financial transactions to telecommunications, that extra second can cause glitches. There's been ongoing debate about whether to abolish leap seconds and let UTC gradually drift from solar time, or to continue inserting them despite the technical challenges they create. For now, leap seconds remain part of our timekeeping system, a reminder that even in our age of atomic precision, we remain connected to the ancient rhythm of Earth's rotation. The second was redefined in 1967 using cesium-133 atomic vibrations. For centuries, the second was defined as a fraction of a day, specifically 1 divided by 86,400, the number of seconds in a day of 24 hours with 60 minutes per hour and 60 seconds per minute. But this definition tied the second to Earth's rotation, and as we've seen, Earth's rotation is not perfectly regular. As scientific and technological demands for precise timekeeping grew in the 20th century, a more stable definition became necessary. In 1967, the international scientific community redefined the second based on an atomic standard. The new definition declared that 1 second is the duration of exactly 9,192,631,770 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. That's quite a mouthful, but the principle is straightforward. Cesium atoms, when properly prepared and isolated, oscillate between quantum states at an extraordinarily precise and unchanging frequency. This frequency is a fundamental property of cesium atoms, the same everywhere in the universe, unaffected by temperature, pressure, or other environmental factors. By counting these oscillations, we can measure time with remarkable accuracy. The choice of cesium-133 wasn't arbitrary. Cesium was already being used in atomic clocks and had proven reliable. The specific number of oscillations, over 9 billion per second, was chosen to make the new definition of the second as close as possible to the historical definition based on Earth's rotation, ensuring continuity in timekeeping standards. This redefinition of the second marked the first time that a unit of measurement was defined based on quantum mechanics rather than macroscopic phenomena. It reflected both our deeper understanding of atomic physics and our need for precision that transcends the irregularities of astronomical time. Before that, ephemeris time averaged Earth's orbital motion. Before the adoption of atomic time, But after scientists recognized that Earth's rotation wasn't sufficiently regular for precise timekeeping, there was an intermediate standard called ephemeris time. Introduced in 1952 and used until it was superseded by atomic time in the 1970s, ephemeris time was based on Earth's orbital motion around the Sun rather than its rotation on its axis. While Earth's rotation exhibits irregularities, its orbit is far more stable and predictable, governed by the unchanging laws of gravity and planetary motion. Ephemeris time was defined in terms of the tropical year, the time it takes for Earth to complete one orbit relative to the seasons. Specifically, one ephemeris second was defined as a specific fraction of the tropical year 1900. Calculating ephemeris time required careful astronomical observations and complex mathematical computations. Astronomers would observe the positions of the Moon and planets, compare them to theoretical predictions, and use these comparisons to determine how much time had actually elapsed. It was a more consistent standard than rotational time, but it wasn't practical for everyday use because it couldn't be determined in real time. You had to make observations, do calculations, and only then could you know what ephemeris time it had been when you made your observations. Ephemeris time served as a bridge between the old rotational standard and the new atomic standard. It represented a conceptual shift, acknowledging that time needed to be defined by the most regular, predictable phenomena we could measure. Once atomic clocks became sufficiently developed and reliable, they offered an even better solution, providing not only stability and precision but also immediate access to the time standard without the need for astronomical observations and calculations. Atomic clocks count 9,192,631,770 cesium vibrations per second. Inside an atomic clock, the process of measuring time is both elegant and extraordinarily precise. The clock uses a sample of cesium-133 atoms, typically in the form of a gas. These atoms are prepared in a specific quantum state and then exposed to microwave radiation at a frequency close to the natural resonance frequency of cesium. When the microwave frequency exactly matches the cesium atom's transition frequency, the atoms respond in a measurable way, changing their quantum state. The clock uses feedback mechanisms to continuously tune the microwave frequency to this resonance, ensuring it remains locked to the precise frequency at which cesium atoms naturally oscillate. An electronic counter then tallies these oscillations, and when it reaches 9,192,631,770, 1 second has elapsed by definition. The precision is astonishing. The best atomic clocks in existence, advanced optical lattice clocks that use different atoms and techniques, are accurate to better than 1 part in 10 to the 18th power. Such a clock would neither gain nor lose a second over tens of billions of years, longer than the current age of the universe. Even standard cesium clocks used for maintaining time standards are accurate to about 1 second in 100 million years. This precision has practical applications beyond simply knowing what time it is. GPS navigation depends on atomic clocks aboard satellites. The system requires nanosecond timing precision to calculate positions accurately. Telecommunications networks synchronize data transmission using atomic time standards. Scientific experiments, from particle physics to astronomy, often require precise timing. And some tests of fundamental physics, like searching for variations in the fundamental constants of nature or detecting gravitational waves, require the extraordinary stability that only atomic clocks provide. Quartz oscillators introduced in 1927 revolutionized precision timekeeping. Before atomic clocks, Before the space age and the digital revolution, there was a simpler but still remarkable advance in timekeeping technology: the quartz crystal oscillator. Quartz, a common mineral, has a useful property. When you apply an electric voltage to a quartz crystal, it vibrates mechanically at a very precise frequency determined by its size and shape. Conversely, when the crystal vibrates, it generates a small electric signal. This property, called piezoelectricity, makes quartz ideal for timekeeping. In 1927, engineers at Bell Telephone Laboratories built the first quartz crystal clock. The clock used a quartz crystal oscillating at a frequency of around 100,000 cycles per second, far faster than any mechanical pendulum or balance wheel. Electronic circuits counted these oscillations and converted them into seconds, minutes, and hours. Quartz clocks were far more accurate than any mechanical timepiece, maintaining time to within a few thousandths of a second per day. They revolutionized scientific research, enabling experiments that required precise timing. They became the standard for observatories and laboratories. By the 1960s and 70s, miniaturization and mass production brought quartz technology to consumer watches, making highly accurate timekeeping affordable and accessible to everyone. The quartz watch in your drawer, powered by a tiny battery, contains a quartz crystal vibrating at 32,768 cycles per second, a frequency chosen because it's a power of 2 and can be easily divided down electronically to 1 pulse per second. That humble quartz watch is more accurate than the finest mechanical chronometers that 18th century clockmakers spent months crafting by hand, and it costs a tiny fraction as much. Christian Huygens' pendulum clock in 1656 improved accuracy from minutes to seconds per day. Long before quartz and atoms and electronics, there was the pendulum. In 1656, the Dutch scientist Christian Huygens invented the pendulum clock, applying Galileo's earlier observations about the regular period of pendulum swings to create a practical timekeeping device. Galileo had noticed that a pendulum, regardless of how wide its swing, takes the same amount of time to complete each oscillation, at least for small amplitudes. This isochronism, as it's called, makes pendulums ideal for regulating clocks. Huygens' clock used a weight-driven mechanism similar to earlier clocks, but instead of the crude foliot balance that earlier clocks used, his design employed a pendulum to control the rate at which the clock's gears advanced. The result was astonishing. Before Huygens, the best clocks might lose or gain 15 minutes in a day. Huygens' pendulum clock was accurate to within about 15 seconds per day, an improvement of nearly 60-fold. Later refinements, including Huygens' own invention of the cycloidal cheeks that improved pendulum isochronism, pushed accuracy even further. By the 18th century, precision pendulum clocks were accurate to within a second or two per day. These clocks transformed both science and daily life. Astronomers could make much more precise observations, timing events in the sky with unprecedented accuracy. This improved astronomy, which in turn improved navigation, allowing ships to determine their longitude at sea more accurately. The pendulum clock reigned supreme for nearly 3 centuries, from Huygens' invention until the arrival of quartz technology in the 20th century. Its simple elegance, the rhythmic swing of a weighted rod keeping perfect time, marked one of humanity's great technological achievements, a device that brought order and precision to the measurement of time itself, and with it, new understanding of the universe and our place within it. Ancient Egyptians divided night and day into 12 variable hours. Thousands of years ago, long before mechanical clocks or standardized timekeeping, the ancient Egyptians developed one of the earliest systems for dividing the day. They split both daylight and darkness into 12 segments each, creating a 24-part cycle that forms the distant ancestor of our modern 24-hour day. But their hours were very different from ours. Egyptian hours were not fixed in length. Instead, they were temporal hours, meaning they varied with the seasons. A daytime hour in summer, when days were long, might last 75 minutes by our reckoning, while a daytime hour in winter might be only 45 minutes. The same was true for nighttime hours, but in reverse. Winter nights were longer, so nighttime hours stretched out, while summer nights were brief, compressing each hour into a shorter span. This might seem strange to us, accustomed as we are to hours of unchanging length, but it made practical sense for an agricultural society living close to natural rhythms. The daylight hours marked the progression of work and activity from sunrise to sunset. It didn't matter whether those hours were long or short in absolute terms. What mattered was dividing the available daylight into manageable segments. The same principle applied to the night. The Egyptians weren't trying to create an abstract, universal measure of time. They were organizing their days and nights in ways that aligned with the natural cycles of light and darkness. This system of variable hours persisted not just in Egypt but across many cultures for thousands of years, only gradually giving way to our modern system of equal hours as mechanical clocks made precise, constant timekeeping both possible and practical. They tracked stars called decans to measure nighttime passage. To mark the hours of the night, the Egyptians looked to the stars. They identified 36 groups of stars, called decans, distributed along the band of the sky through which the sun appears to travel over the course of a year. Each decan would rise above the eastern horizon in sequence, and by watching which decan was rising, Egyptian priests and timekeepers could determine how much of the night had passed. The system worked because Earth's rotation causes different stars to be visible at different times of night, and Earth's orbit causes different stars to dominate the night sky during different seasons. Over the course of a year, each decan would have its period of prominence, rising at dusk and marking the passage of night. The Egyptians associated each decan with a 10-day period, and they used these star groups not just for timekeeping but also for their calendar and for astrological purposes. Observing the decans required clear skies and knowledge passed down through generations, the ability to recognize star patterns and understand their movements. This celestial timekeeping connected the Egyptians to the cosmos in a direct, observable way. Every clear night, the rotation of the heavens provided a clock face, with the decans serving as our markers slowly wheeling across the sky. The system had limitations. Clouds obscured the stars. Moonlight could make fainter stars difficult to see. And as the stars shifted slightly over centuries due to precession, the slow wobble of Earth's axis, the decan system gradually drifted out of alignment. But for millennia, these star groups served as humanity's nighttime clock, proof that ancient peoples were keen observers of the sky, finding patterns and meaning in the wheeling constellations above them. The Sumerians divided circles into 360 degrees, influencing 60-minute hours. More than 5,000 years ago, the ancient Sumerians of Mesopotamia developed a mathematical system based on the number 60. We call this a sexagesimal system, and its influence extends into our lives today. The Sumerians chose base 60 for practical reasons. Unlike our base 10 system, which can only be evenly divided by 2, 5, and 10, the number 60 can be divided evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes calculations and fractions much easier to handle without decimal points. When merchants needed to divide goods or calculate proportions, base 60 gave them flexibility and precision. The Sumerians applied this system to measuring angles and circles, dividing a circle into 360 degrees. Why 360? It's close to the number of days in a year, which may have made it feel natural and cosmologically significant. It's also highly divisible, being 6 times 60. This angular measure spread to neighboring cultures, was adopted by the Babylonians, who inherited and developed Sumerian mathematics, and eventually made its way to the Greeks and then to us. The same sexagesimal system influenced how we measure time. When medieval scholars and clockmakers needed to subdivide hours, they turned to the ancient Mesopotamian system, dividing each hour into 60 minutes and each minute into 60 seconds. The words minute and second come from Latin phrases meaning the first small part and the second small part. So every time you glance at a clock and see 60 minutes in an hour, you're inheriting a system of thought that originated in ancient Mesopotamia, a mathematical legacy that has endured for more than 5 millennia, embedded so deeply in how we understand circles, angles, and time that we rarely stop to question why we don't divide hours into 100 minutes or circles into 100 degrees. The Gregorian calendar corrected leap year drift in 1582. By the 16th century, Europe had a problem. The Julian calendar, introduced by Julius Caesar in 45 BCE, had served for over 1,600 years. It established a system of 365-day years with an extra day added every 4th year, creating leap years to account for the fact that Earth's orbit takes about 365.25 days. But 365.25 is only an approximation. The true length of a tropical year, the time from one spring equinox to the next, is about 365.2422 days, roughly 11 minutes shorter than the Julian calendar assumed. Those 11 minutes per year don't sound like much, but over centuries they accumulated. By 1582, the calendar had drifted about 10 days out of alignment with the seasons. The spring equinox, which should occur around March 21st, was happening on March 11th. This created problems for calculating Easter, which is determined by the spring equinox and the phases of the moon. Pope Gregory XIII commissioned a reform to correct the drift. A team of scholars and astronomers, led by the Jesuit mathematician Christopher Clavius, developed a refined leap year system. The new Gregorian calendar kept the basic structure of leap years every 4 years, but added a crucial refinement. Years divisible by 100 would not be leap years unless they were also divisible by 400. This meant that 1700, 1800, and 1900 were not leap years, but 2000 was. This seemingly small change brought the calendar much closer to the true length of the tropical year, reducing the error to just 1 day in about 3,000 years. To implement the reform, 10 days had to be dropped. October 4th, 1582, was followed immediately by October 15th. Not everyone accepted the new calendar immediately. Protestant countries resisted for decades or even centuries, seeing it as a Catholic imposition. But eventually, the Gregorian calendar's superior accuracy won out, and today it serves as the civil calendar for nearly the entire world. Leap years add a day to align calendars with Earth's 365.24-day orbit. Earth's journey around the Sun doesn't take a convenient, whole number of days. If we used a 365-day calendar every year, the calendar would gradually drift relative to the seasons. After 4 years, we'd be nearly a full day out of sync. After a century, the drift would be substantial. Summer would gradually creep into what the calendar said was spring. The agricultural cycles that human civilization depends on would no longer align with the calendar dates. The solution is the leap year, an extra day inserted into the calendar every 4 years to compensate for the quarter-day difference between our 365-day calendar and Earth's actual orbital period. We add this extra day at the end of February, making it 29 days long instead of the usual 28. This keeps the calendar aligned with the seasons over the long term. But as we just discussed, even the 4-year cycle isn't quite perfect. That's why we need the additional rule about centuries. The Gregorian refinement, skipping leap years in most century years but including them when the year is divisible by 400, brings us very close to Earth's true orbital period. Still, even the Gregorian calendar will eventually drift. In about 3,000 years, it will be off by 1 day. Future civilizations, if they're still using our calendar system, might need to make further adjustments. Or perhaps by then, humanity will have developed entirely new ways of organizing time, new calendars based on different principles, or maybe even abandoned Earth's year as a reference altogether if we've spread to other worlds with different orbital periods. For now, though, the leap year system works remarkably well, keeping our calendars synchronized with the seasons, ensuring that spring arrives when we expect it, that summer follows spring, and that the cycle of the year remains aligned with the ancient rhythms of our planet's journey around the sun. The Mayan long count calendar spans 5,125-year cycles. The ancient Maya of Central America developed one of the most sophisticated calendar systems in human history. While they used several interlocking calendars for different purposes, including a 260-day ritual calendar and a 365-day solar calendar, their most ambitious timekeeping system was the long count. This calendar was designed to track vast spans of time, far beyond human lifetimes or even the spans of civilizations. The long count measures time from a mythological creation date, which corresponds to August 11th, 3114 BCE in our calendar. From this starting point, the Maya counted days using a modified base 20 system. The basic unit was the kin, 1 day. 20 kin made a uinal, roughly a month. 18 uinal made a ton, approximately a year. 20 ton made a katan, about 20 years. And 13 katan made a baktan, roughly 394 years. A complete cycle of the long count consists of 13 baktans, totaling about 5,125 years. The completion of this great cycle, which occurred on December 21, 2012, received considerable attention, with some interpreting it as a prediction of apocalypse. But the Maya themselves saw it as simply the turning of a great wheel, the end of one era and the beginning of another. Time would continue, cycling through another 5,125-year period. The long count reflects a conception of time as both linear and cyclical, with vast cosmic ages unfolding one after another. Mayan monuments often recorded long count dates, precisely marking when they were erected according to this grand timescale. The system demonstrates the Mayas' advanced mathematics and their concern with placing events within a broader cosmic context, seeing the present moment as part of immense cycles stretching back to creation and forward into the distant future. The Hindu Kali Yuga lasts 432,000 years. Hindu cosmology envisions time operating at scales that dwarf even the Mayan long count. According to traditional Hindu texts, time unfolds in vast cosmic cycles called yugas. There are 4 yugas that repeat in sequence: the Satya Yuga or Golden Age, the Treta Yuga, the Dvapara Yuga, and finally the Kali Yuga, the current age of darkness and decline. The Kali Yuga is said to last 432,000 years. We are, according to traditional reckoning, only about 5,000 years into this age, which began around 3102 BCE. After the Kali Yuga ends, the cycle will begin anew with another Satya Yuga. But that's just one level of Hindu cosmic time. 4 yugas together make a Mahayuga, lasting 4.32 million years. 1,000 Mahayugas make a Kalpa, also called a day of Brahma, lasting 4.32 billion years. And Brahma himself lives for 100 years of such days, meaning the total lifespan of the universe in this system is 311.04 trillion years. These numbers boggle the mind. They express a vision of cosmic time in which human history, all of recorded civilization, is less than the blink of an eye. Entire species, continents, geological ages rise and fall within the span of a single yuga. These vast temporal scales aren't meant to be literally measured or empirically verified. They're conceptual tools, ways of thinking about existence that place human life within an almost unimaginably large context. They remind us that from the perspective of cosmic time, our troubles and triumphs are fleeting, that the universe operates according to rhythms far slower and grander than we can directly perceive. In modern times, it's striking that some of these ancient numbers aren't far off from scientific estimates. The 4.32 billion year Kalpa, for instance, is remarkably close to the actual age of Earth, about 4.5 billion years, a coincidence that some find meaningful and others attribute to chance. The Jewish calendar blends lunar and solar cycles. Many calendar systems are based either on the moon's phases or the sun's annual journey, but the Jewish calendar incorporates both. Months are lunar, beginning with the new moon and lasting about 29 or 30 days. 12 such months add up to only about 354 days, falling short of the solar year by about 11 days. If the calendar simply followed the moon, it would drift through the seasons, with holidays occurring at different times of year over time. To prevent this drift, the Jewish calendar adds a leap month 7 times within every 19-year cycle. This intercalation keeps the calendar synchronized with the seasons, ensuring that Passover, for instance, always falls in the spring. The system of inserting leap months is quite clever. In years 3, 6, 8, 11, 14, 17, and 19 of the 19-year cycle, an extra month called Adar 2 is inserted. The 19-year cycle works because 19 solar years and 235 lunar months are almost exactly the same length, a relationship known as the Metonic cycle, discovered by the ancient Greek astronomer Meton. The Jewish calendar has been used for religious purposes for over 1,600 years in its current form, though its origins are much older. It determines the dates of Jewish holidays and observances, and it's still used alongside the civil Gregorian calendar by Jewish communities worldwide. Dates in the Jewish calendar are counted from the traditional date of creation, which corresponds to 3761 BCE in the Gregorian calendar. So while we're in the year 2025 CE, the Jewish year at this time is 5785. This calendar represents an elegant solution to the problem of reconciling lunar and solar cycles, creating a system that honors both the monthly rhythm of the moon and the yearly cycle of the seasons. The French Revolutionary calendar replaced weeks with 10-day decades. In 1793, In the midst of the French Revolution, the revolutionary government decided that even the calendar itself needed to be reformed. The traditional calendar, with its saints' days and religious associations, seemed incompatible with the revolution's secular ideals. A commission was formed to create an entirely new calendar, rational and based on decimal principles. The result was the French Revolutionary Calendar, which took effect in October 1793 and dated its era from September 22, 1792, the founding of the First Republic. The revolutionary calendar abolished weeks. Instead, each month was divided into 3 decades of 10 days each. Each day of the decade was numbered, with the 10th day, Decady, being a day of rest. There were 12 months of 30 days each, and to make up the remaining days of the year, 5 or 6 complementary days were added at the end, designated as holidays. The months were given new names reflecting the seasons and nature. Vendémiaire for the harvest, Brumaire for fog, Frimaire for frost, Nivose for snow, and so on through the year. Even the hours, minutes, and seconds were decimalized in some proposals, with the day divided into 10 decimal hours, though this proved too impractical to implement widely. The revolutionary calendar was used officially for about 12 years. Napoleon abolished it in 1806, returning France to the Gregorian calendar. The decimal calendar simply didn't align with the weekly rhythms that people were accustomed to, and the 10-day week meant that rest days came less frequently than in the traditional 7-day week, which proved unpopular. The revolutionary calendar stands as a fascinating experiment, an attempt to remake time itself according to rational principles, ultimately defeated by the weight of tradition and the practical needs of daily life. Sweden once skipped 11 days and added a leap day, enraging the public. When the Protestant regions of Europe finally began adopting the Gregorian calendar in the 17th and 18th centuries, decades or even more than a century after Catholic countries had made the switch, they faced a dilemma. The calendar drift had continued during all those years of resistance, meaning they now had to drop even more days to realign with the seasons and with the calendar used by much of the rest of Europe. Most countries simply bit the bullet and dropped 10, 11, or 12 days all at once. But Sweden tried a different approach, one that turned into a disaster. In 1700, Sweden decided to gradually phase out the Julian calendar by skipping all leap days over a 40-year period until they were aligned with the Gregorian calendar. They successfully skipped the leap day in 1700, making that year only 365 days long. But then wars and changes in government disrupted the plan. The leap days in 1704 and 1708 were added back in, contrary to the original plan. By 1712, Sweden was out of sync with everyone. They weren't using the Julian calendar anymore, having dropped one leap day, but they hadn't adopted the Gregorian calendar either. They were in a confused state, using a calendar that nobody else in the world was using. To fix this mess, Sweden decided to revert to the Julian calendar. To do this, they added an extra leap day in 1712, creating a February 30th that year. Then in 1753, Sweden finally gave up on gradual transitions and adopted the Gregorian calendar all at once, dropping 11 days overnight. February 17th, 1753, was followed immediately by March 1st. The public was outraged by the confusion and chaos. The botched calendar reform had disrupted contracts, caused confusion about dates and anniversaries, and created administrative nightmares. Sweden's experience became a cautionary tale about the importance of clear, decisive action when making major changes to fundamental systems like calendars, systems so embedded in daily life that half measures and compromises only create confusion and frustration that ripple through every level of society. Human bodies run on circadian rhythms regulating sleep and hormones. Deep within nearly every cell of your body, molecular clocks are ticking. These biological timekeepers, known as circadian rhythms, orchestrate a vast array of physiological processes according to a roughly 24-hour cycle. The word circadian comes from the Latin circa diem, meaning about a day. Even without any external cues, isolated in constant darkness, your body maintains these rhythms, though they might drift slightly from exactly 24 hours. The master clock resides in a tiny region of the brain called the suprachiasmatic nucleus, located just above where the optic nerves cross. This cluster of about 20,000 neurons receives information about light levels directly from the eyes and uses this information to synchronize your internal rhythms with the external day-night cycle. When the suprachiasmatic nucleus detects that it's evening, it signals the pineal gland to begin producing melatonin, the hormone that promotes sleepiness. As morning approaches, melatonin production decreases, and other hormones like cortisol increase, helping you wake up and become alert. But sleep and wakefulness are just the most obvious manifestations of circadian control. Your body temperature follows a daily rhythm, reaching its lowest point in the early morning hours and its peak in the late afternoon. Blood pressure, immune function, digestion, cell division, even your sensitivity to pain, all fluctuate according to circadian cycles. These rhythms evolved over billions of years as life adapted to the reliable cycle of day and night created by Earth's rotation. Disrupting these rhythms, through shift work or jet lag or simply staying up too late staring at bright screens, can have real health consequences. Your body expects certain things to happen at certain times, and when you force it to operate against its natural rhythms, various systems can become desynchronized, potentially affecting everything from mood to metabolism to long-term health. Bioluminescent bacteria synchronize flashes on daily cycles. Circadian rhythms aren't unique to humans or even to complex organisms. Even single-celled bacteria possess molecular clocks that allow them to track the passage of time. Some of the most striking examples come from bioluminescent bacteria, microorganisms that produce light through chemical reactions. Certain species of these bacteria have been found to synchronize their light production according to daily rhythms. In laboratory conditions, populations of these bacteria will flash more brightly at certain times of day and dim at others, maintaining this pattern even when kept in constant darkness and temperature. The bacteria possess gene networks that oscillate with a roughly 24-hour period, driving the production of light-emitting compounds at specific times. This might seem puzzling. Why would a bacterium need to know what time it is? But circadian rhythms offer advantages even to simple organisms. They allow the bacterium to anticipate regular environmental changes, preparing in advance rather than simply reacting. A bacterium might activate genes for photosynthesis just before dawn, or prepare for nutrient scarcity during night. These rhythms can help bacteria coordinate with the organisms they interact with, whether as symbionts, parasites, or free-living organisms affected by the daily cycles of their environment. The fact that even bacteria possess circadian clocks tells us something profound about the nature of time and life. The daily rotation of Earth has been a constant feature of our planet for billions of years, and life at every level of complexity has evolved mechanisms to track and anticipate this cycle. From bacteria to plants to insects to humans, we are all connected by this shared temporal framework, all dancing to the rhythm of Earth's rotation, all carrying within ourselves molecular echoes of the day-night cycle that has shaped life since its earliest beginnings. Animals perceive time differently. Flies see far more frames per second than humans. Time is not experienced the same way by all creatures. What feels like a second to you is perceived very differently by a fly. This isn't just a metaphor or a matter of subjective feeling. It's rooted in the neurobiology of perception, particularly in how quickly nervous systems can process information. Visual perception provides a clear example. Humans perceive motion as smooth and continuous when it occurs at rates faster than about 60 frames per second. This is why movies, which typically show 24 frames per second, appear to show fluid motion rather than a series of still images, especially with motion blur and other techniques. But flies process visual information much faster. A fly's visual system can distinguish individual flickers at rates exceeding 250 times per second. What appears to us as a continuously glowing light appears to a fly as a rapid strobe. When you try to swat a fly, your hand seems to move slowly from the fly's perspective. The fly has more time, subjectively, to react and escape. Its faster neural processing effectively stretches time, giving it more subjective moments within each objective second. This variation in temporal perception extends across the animal kingdom. Small animals with high metabolic rates generally perceive time as passing more slowly, processing more information per unit of objective time. Large animals with slower metabolisms tend to process information more slowly, experiencing fewer subjective moments per second. A mouse darting away from a predator experiences a different temporal landscape than an elephant lumbering through the forest. These differences reflect evolutionary adaptations. A small animal that must evade fast predators benefits from rapid information processing. The cost is high energy consumption. The brain is metabolically expensive, and processing information quickly requires substantial resources. Each species has evolved the temporal resolution that suits its ecological niche, creating a world where time flows at different rates for different creatures sharing the same physical space. Humans do not directly sense time but infer it from memory and attention. We have senses for light, sound, touch, taste, and smell. But we have no sense organ dedicated to perceiving time. There is no temporal receptor in your body sending signals to your brain saying 200 milliseconds have passed or it's been 5 minutes. Yet you clearly have some sense of time passing. You can estimate durations. You know that some events last longer than others. You experience the flow of time from moment to moment. How does this work? Time perception is constructed by your brain from various sources of information. One crucial element is memory. Your sense of how much time has passed depends partly on how many memories you formed during that interval. When you're engaged in a novel, stimulating activity, your brain forms many detailed memories. Looking back later, that period seems to have lasted a long time because there's so much memory content associated with it. But when you're bored, doing routine activities that don't require much attention, you form fewer memories, and looking back, that period seems to have passed quickly. This creates a paradox. While you're bored, time seems to drag. Minutes feel like hours. But looking back later, that boring afternoon seems to have passed in a flash because you have few memories of it. Conversely, an exciting vacation flies by while you're experiencing it, but later it seems like it lasted much longer because you formed so many rich memories. Attention also plays a crucial role. When you're focused on time itself, constantly checking your watch or waiting for something, time seems to pass slowly. Your attention magnifies the perception of duration. But when you're absorbed in an activity, your attention directed elsewhere, you lose track of time. Hours can pass without your noticing. Your brain constructs your experience of time from these various sources: memory formation, attention, emotional state, even metabolic factors like body temperature. Time perception is an inference, a construction, not a direct sensation. This is why time can feel so fluid, so variable, so different depending on what you're doing and how you're feeling. Strong emotions and novelty distort perceived duration. Fear stretches time. Studies have shown that people experiencing frightening situations, like falling or being in an accident, often report that time seemed to slow down, that events unfolded in slow motion. This isn't because time actually slowed or because they processed visual information faster like a fly does. It's because fear triggers intense attention and memory formation. When you're frightened, your amygdala, the brain region involved in emotional processing, becomes highly active. This heightened emotional state causes your brain to encode memories in much greater detail. You notice more, remember more, and when you recall the event later, it seems to have lasted longer than it objectively did because there's so much memory content packed into that brief span. The effect can work in reverse during the event itself. Some people report time speeding up during intense, frightening experiences, perhaps because they're so overwhelmed that they can't process information normally. Novelty has a similar effect to fear, though less intense. When you're experiencing something new, your brain pays close attention, forming detailed memories. The first time you drive to a new location, the trip seems to take a long time. But after you've made the journey many times, it becomes routine. You pay less attention, form fewer memories, and the same drive seems much shorter. This is why childhood seems to have lasted so long when we look back on it. Everything was new. You were constantly learning, constantly encountering novel situations that demanded attention and created rich memories. As adults, much of life becomes routine, and time seems to accelerate as a result. Strong emotions and novel experiences stand out in memory, creating temporal landmarks that stretch our subjective sense of how much time has passed, while routine and familiar experiences blend together, creating the sensation that time is flying by. Psychological time speeds up with age as experiences become routine. There's a common observation that time seems to pass more quickly as we get older. Years that felt endlessly long in childhood fly by in adulthood. There are several explanations for this phenomenon, and they likely all contribute to the effect. One explanation involves the proportional theory. When you're 5 years old, 1 year represents 20% of your entire life. It's a substantial fraction of your existence. When you're 50, 1 year is only 2% of your life. Each additional year is a smaller proportion of your total experience, so it feels less significant, passes more quickly. Another explanation relates to novelty and routine, as we just discussed. Children are constantly encountering new experiences, learning new skills, visiting new places. This novelty demands attention and creates detailed memories, making time seem to pass slowly. Adults, having established routines and familiar patterns, experience less novelty. Days blend together. Without distinct memories to mark the passage of time, it seems to accelerate. There may also be metabolic factors. Children have faster metabolisms and higher heart rates than adults. Some researchers have suggested that these physiological differences might affect the subjective perception of time's passage, though this remains speculative. Whatever the exact mechanisms, the subjective acceleration of time with age is nearly universal. It's one reason why many people feel a sense of urgency as they grow older, a desire to make each day count, to avoid falling into routines that make years evaporate. The awareness that time seems to be speeding up can prompt us to seek out new experiences, to travel, to learn new skills, to deliberately create the kind of novelty and engagement that restores, at least temporarily, that childhood sense of time stretching out before us, full of possibility and rich with experience. Understanding the psychology of time perception gives us tools to shape our experience, to slow down our subjective time by choosing attention and presence over routine and distraction. Cave isolation experiments stretched human internal clocks dramatically. In the 1960s and 70s, scientists conducted remarkable experiments to understand human circadian rhythms. Volunteers would spend weeks or even months living in caves or specially constructed underground apartments, isolated from all time cues. No sunlight, no clocks, no schedules imposed from outside. They could sleep and wake whenever they felt like it, eat when hungry, work or read or rest according to their own inclinations. The experimenters monitored them continuously, recording their sleep-wake cycles and other physiological measures. The results were surprising. Without external time cues, human circadian rhythms drifted away from 24 hours. Most subjects settled into cycles of about 25 hours or slightly longer. Some drifted even further, developing sleep-wake cycles of 30 or even 36 hours. One famous subject, French cave explorer Michel Siffre, spent 2 months in a cave and emerged convinced that only 25 days had passed. His internal sense of time had stretched dramatically. During his isolation, Siffre's days had lengthened, and he'd experienced fewer sleep-wake cycles than he would have above ground. These experiments demonstrated that while humans have internal circadian clocks, these clocks need to be synchronized to the external world through environmental cues, particularly light. Without those cues, we drift, and our subjective experience of time becomes unmoored from objective clock time. The studies also revealed that different physiological processes can desynchronize from each other during isolation. Your sleep-wake cycle might drift to 25 hours while your body temperature rhythm remains closer to 24 hours. The various internal clocks that normally work together in harmony can come apart when deprived of external synchronizing signals. These cave experiments gave us deep insights into how human time perception works, how our bodies naturally organize temporal experience, and how dependent we are on the rhythmic cues of light and darkness to keep our internal clocks aligned with the world around us. Pathological conditions further distort time perception. Brain injuries, neurological disorders, and psychiatric conditions can profoundly alter how people experience time. Patients with damage to certain brain regions may lose the ability to estimate durations or sequence events. Someone might be unable to tell whether 2 seconds or 20 seconds have passed, or might struggle to determine whether they ate breakfast before or after getting dressed. Parkinson's disease, which affects dopamine-producing neurons in the brain, often impairs time perception. Patients may underestimate how much time has passed, making seconds seem shorter than they are. This likely relates to dopamine's role in timing and motor control. Depression often creates a sense that time is dragging, that hours stretch out endlessly. This might relate to the attentional effects we discussed earlier. Depression tends to focus attention inward, on negative thoughts and feelings, and this heightened attention to one's internal state can make time feel slow. Schizophrenia can fragment time perception, making it difficult to maintain a coherent sense of temporal flow. Some patients report experiencing moments in the wrong order or feeling that past and present are blending together. Certain drugs dramatically alter time perception. Cannabis often makes time seem to slow down. Stimulants like amphetamines can speed up internal clocks, making external time seem slow by comparison. Psychedelics can produce even more profound distortions, sometimes creating experiences that seem to last for hours or even years despite occurring within minutes of objective time. These pathological and drug-induced alterations reveal just how much our normal experience of time depends on specific neural circuits and neurochemical systems functioning properly. Time perception isn't a single sense but a complex construction involving multiple brain regions and processes. When any part of this system malfunctions, our experience of temporal reality can become strange, distorted, even frightening, reminding us that the smooth flow of time we normally experience is an achievement, a careful orchestration by neural systems working together to create our temporal consciousness. Light from your own nose takes microseconds to reach your brain, meaning everyone lives slightly in the past. Every experience you have of the present moment is actually an experience of the very recent past. This isn't philosophy. It's neurobiology. When light hits your retina, it triggers a cascade of chemical and electrical signals that must travel from your eye to your visual cortex at the back of your brain. This takes time, somewhere between 20 and 40 milliseconds depending on various factors. Your brain then needs additional time to process this raw visual information, to identify objects, recognize faces, understand what you're seeing. By the time you become consciously aware of seeing something, at least 80 to 100 milliseconds have passed since the light entered your eye. Similar delays affect all your senses. Touch signals must travel from your skin to your brain along nerve fibers. Sound must be processed by your auditory system. All of this takes time. Your brain does something remarkable to compensate for these delays. It doesn't present your conscious experience as a scattered collection of sensations arriving at different times. Instead, it synchronizes everything, creating the illusion of a unified present moment even though the various pieces of information arrived at different times and from different sources. Your brain also predicts the immediate future, using past patterns to anticipate where objects are going and what's about to happen. When you catch a ball, you're not really responding to where the ball is at the moment you perceive it. You're responding to where your brain predicts it will be by the time your motor commands reach your hand. In a sense, we all live slightly in the past, perceiving events not as they happen but after a small delay required for neural processing. Yet our brains are so good at compensating for this lag, at predicting and synchronizing and creating coherence, that we never notice the delay. We feel present, immediate, synchronized with reality, even though we're always experiencing an echo, a neural reconstruction of events that happened a fraction of a second ago. Dreams unfold temporally despite lacking physical space. When you dream, you experience events unfolding in time. You move through dream narratives, things happen in sequence, conversations occur, actions lead to consequences. Yet there's no physical space in which these dreams occur. Your sleeping body lies still in bed. Nothing is actually happening in external reality. The temporal flow of dreams exists purely as neural activity, patterns of firing neurons in your brain creating the subjective experience of events unfolding over time. This reveals something profound about the nature of time and consciousness. Time, at least as we experience it subjectively, doesn't require external physical events. Your brain can generate temporal experience internally. In dreams, minutes or hours can seem to pass, yet you might have been asleep for only a few minutes. Conversely, dreams that seem to last only moments might occur during lengthy periods of REM sleep. The relationship between dream time and clock time is loose and variable. The temporal structure of dreams also differs from waking experience. Dreams often jump discontinuously from one scene to another. Events that would be impossible or would take hours in reality occur instantly. You might be in one location and then suddenly, without any sense of having traveled, be somewhere completely different. Past, present, and sometimes future blend together. Dead relatives appear alive. Childhood memories mix with recent events. Yet despite this temporal chaos, dreams still have a narrative flow, a sense of progression, a before and after. Your dreaming mind constructs causality and sequence even when the content is bizarre and impossible. Dreams demonstrate that temporal experience is fundamentally a creation of consciousness, a way our minds organize and structure experience. The flow of time we perceive, whether awake or dreaming, is constructed by neural processes that create sequence, duration, and narrative from the continuous stream of brain activity. In this sense, all time is psychological time. All moments are created by the mind interpreting its own activity, and the division between objective and subjective time becomes blurred, perhaps even meaningless, when we recognize that our entire experience of temporal flow exists only within consciousness itself. Language shapes how cultures conceptualize time, mapping it horizontally or vertically. The words we use to talk about time reveal deep patterns in how different cultures think about temporal experience. In English and most European languages, we speak of time using horizontal spatial metaphors. We look forward to the future and back to the past. Events lie ahead of us or behind us. Time stretches out along a horizontal line. This metaphorical structure is so ingrained that it feels natural, inevitable. But not all languages organize time this way. The Aymara people of the Andes use the opposite orientation. For them, the past is in front, because you can see it, you know what happened. The future is behind you, unseen, unknown, approaching from where you cannot look. Speakers of Aymara gesture forward when discussing the past and backward when discussing the future, a reversal that highlights how arbitrary our own convention is. Mandarin Chinese uses both horizontal and vertical metaphors for time. While horizontal metaphors exist, Mandarin speakers also commonly describe time vertically. The word for last month literally means up month, while next month is down month. Earlier events are described as up, later events as down. This vertical structuring of time appears in other aspects of Chinese culture as well, from calendars to genealogies. Some languages have even more unusual temporal structures. The Pormpura, an Aboriginal community in Australia, orient time according to absolute cardinal directions rather than relative to the speaker's body. Events might be described as happening to the east or west, and how people gesture about time depends on which direction they're facing. Someone facing south would gesture leftward for the past, but the same person facing north would gesture rightward for the past, because east and west have switched sides. These linguistic differences aren't just curiosities. Research suggests they actually influence how people think about and process temporal information. Mandarin speakers, accustomed to vertical time metaphors, are faster at processing temporal information when it's presented vertically. The language we speak shapes the conceptual frameworks we use to understand time, demonstrating that even something as fundamental as temporal experience is filtered through cultural and linguistic structures that vary across human societies. Week derives from Babylonian planetary assignments. The 7-day week is so familiar that we rarely question it. But unlike days, which correspond to Earth's rotation, or months, which roughly correspond to the moon's cycle, or years, which match Earth's orbit, the week has no astronomical basis. It's a purely cultural creation, and its origins lie in ancient Mesopotamia. The Babylonians, inheriting and developing earlier Sumerian traditions, identified 7 celestial objects that moved against the background of fixed stars: the Sun, the Moon, Mars, Mercury, Jupiter, Venus, and Saturn. These 7 wanderers, as they appeared from Earth, seemed special, divine. The Babylonians associated each with a god and assigned each to rule over one day in a repeating 7-day cycle. This system spread to other cultures. The Romans adopted it, assigning their own gods to the days. When this Roman week reached Germanic peoples, they substituted their own deities for the Roman gods, which is why our English day names are a mix of Roman and Germanic influences. Sunday and Monday retain their celestial names, the Sun's Day and Moon's Day. Tuesday through Friday honor Germanic gods, Ty, Woden, Thor, and Frigg, roughly equivalent to Roman Mars, Mercury, Jupiter, and Venus. Saturday keeps the Roman god Saturn's name. The 7-day week has no practical basis in nature. Other cultures have tried different lengths. The ancient Egyptians used 10-day weeks. The French Revolutionary calendar, as we discussed, used 10-day decades. The Soviet Union briefly experimented with 5-day and 6-day weeks. But none of these alternatives caught on. The 7-day week, originating in Babylonian astrology over 2,500 years ago, has proven remarkably persistent, spreading across the world and becoming the standard unit for organizing time beyond the day, a legacy of ancient stargazers who saw divine significance in the 7 wandering lights moving across the heavens. Fortnight means 14 nights in Old English. The word fortnight, common in British English and less familiar in American usage, simply means a period of 14 days or 2 weeks. Its etymology is straightforward. It contracts 14 nights from Old English. But why measure time in nights rather than days? This reflects an ancient convention of counting nights instead of days, a practice found in many early Germanic cultures and preserved in various linguistic fossils. The Old English and Germanic peoples often reckoned time by nights rather than days, perhaps because darkness was the more noticeable marker of time's passage, the point when daily activities ceased and the household gathered together. Counting by nights also appears in other English expressions. When we say something happened a sennight ago, a now archaic term, we mean a week ago, literally 7 nights. The practice of counting nights is also found in other Indo-European languages and cultures. The ancient Celts counted time in nights, which is why Halloween, Samhain in Irish, marks the eve or night before All Saints' Day. The night was considered the beginning of the day rather than its ending. This custom has mostly faded from English, but fortnight remains, a commonplace word preserving an ancient way of thinking about time. In an era when we primarily organize time by the clock and calendar, by precisely measured hours and days, fortnight connects us to older patterns of thought, when people lived more closely with the rhythms of darkness and light, when the falling of night marked a boundary more significant than the arbitrary division of one date from the next on a calendar. The word reminds us that even our most ordinary language carries within it the layered history of how humans have understood and measured time over millennia. Vikings measured time using rope shadows. In the age before mechanical clocks, before standardized timekeeping, people developed ingenious methods for tracking the passage of time during the day. The Vikings, seafaring peoples of medieval Scandinavia, used simple yet effective devices to measure time, particularly during their long ocean voyages where knowing time was crucial for navigation. One such device was the Viking sun compass, which worked in conjunction with a gnomon, a vertical stick or post. As the sun moved across the sky, the gnomon's shadow would rotate and change length. By marking the shadow's position at different times, the Vikings could track the hours. But for more precise timekeeping, some sources suggest Vikings used a kind of rope or knotted cord. By stretching a rope horizontally and watching how the shadow from a vertical post moved along the rope's length, they could divide the day into segments. The shadow would progress along the rope as the hours passed, with marks or knots indicating particular times. The accuracy of such a system depended on several factors: the latitude, the season, and careful calibration. It wouldn't work on cloudy days, and it would be useless during the twilight or darkness of northern winters. But for summer sailing under clear skies, shadow measurement provided Vikings with a way to coordinate activities, to know when to change shifts, when to expect arrival at destinations. These simple shadow clocks connect to a long tradition of solar timekeeping found across many cultures. Sundials, in their various forms, were used throughout the ancient and medieval world. The Vikings' rope shadows represent a portable, practical adaptation of this principle, suitable for life aboard ships where more elaborate devices would be impractical. They remind us that even without sophisticated technology, careful observation of natural phenomena could provide the temporal information people needed to navigate their world. Anglo-Saxons measured time in tides. The Anglo-Saxons, the Germanic peoples who settled in Britain during the early medieval period, had their own distinctive system for dividing the day. They divided the 24-hour cycle into 8 tides, each lasting 3 hours. The word tide in Old English meant time or season, a meaning preserved in expressions like Yuletide and Eventide. These 8 tides had specific names: morning tide, daytime, noon, afternoon, evening, night, midnight, and the hours before dawn each had their designation. This division reflected the natural rhythms of daily life, marking the major transitions in activity and light. Morning tide was the time for rising and beginning work. Noon marked midday, the point when the sun reached its highest position and work might pause for a meal. Evening signaled the end of the workday and the approach of night. This system, like many pre-modern timekeeping methods, was not concerned with precise minute-by-minute accuracy. It organized time into meaningful segments defined by activities and natural phenomena. You didn't need to know the exact hour. You needed to know whether it was time to work in the fields, time to eat, or time to sleep. The tidal system also reflects the Anglo-Saxon connection to the sea and to tidal rhythms, though the 8 tides of the day shouldn't be confused with ocean tides, which follow the moon cycle rather than the sun's daily path. Still, for coastal peoples, the ebb and flow of the sea provided another natural clock, one that operated on a different cycle from the solar day. By the late medieval period, as mechanical clocks began to appear and timekeeping became more standardized across Europe, the old tidal system gradually faded from use. But it persisted in rural areas and in customary practices long after urban centers had adopted hour-based timekeeping, a reminder that human cultures have developed many different ways of carving up the day, each reflecting the practical needs and natural observations of particular times and places. Medieval monks used temporary hours tied to daylight. In medieval monasteries across Europe, the rhythm of life was organized around prayer. The monastic day was divided into canonical hours, specific times for communal worship. Matins in the middle of the night, lauds at dawn, prime, terce, sext, none in the afternoon, vespers at sunset, and compline before bed. These hours weren't spaced equally in terms of modern clock time. Instead, they were tied to the natural cycle of daylight. Terce meant the third hour after sunrise, sext the sixth hour, none the ninth. The actual clock time when these prayers occurred varied with the seasons. In summer, when days were long, the hours between sunrise and sunset stretched out. Each canonical hour occurred later in terms of absolute time. In winter, when days were short, the hours compressed. This system of temporary or seasonal hours, which we encountered earlier when discussing ancient Egypt, persisted in Europe throughout the medieval period. It made practical sense for agricultural societies living close to natural rhythms, where the relevant fact was how much daylight remained for work rather than what arbitrary number a clock showed. Monks needed to perform their prayers at the appropriate liturgical times, synchronized with dawn and dusk. The precise duration of an hour was less important than maintaining the rhythm of the divine office, the cycle of prayer that structured monastic life. This began to change with the development of mechanical clocks in the 14th century. Early mechanical clocks in monasteries helped monks time their prayers more precisely. But these clocks initially marked temporary hours, speeding up and slowing down to match the changing length of daylight through the seasons. Only gradually did society shift to equal hours of fixed length, as mechanical timekeeping and the needs of commerce and coordination made standardized time more useful than time tied to the sun's actual position in the sky. Incan quipus encoded time alongside numbers. The Inca Empire, which flourished in South America in the 15th and early 16th centuries, developed a sophisticated record-keeping system without ever inventing writing as we understand it. Instead, they used quipus, arrays of knotted strings that encoded information through the placement, type, and color of knots, as well as the arrangement of pendant cords hanging from a primary cord. Quipus were primarily used for accounting, recording census data, tribute payments, and other numerical information important for administering a vast empire. Different types of knots represented different numbers, and the position of knots on the string indicated place value in a base 10 system. But quipus encoded more than just quantities. Recent research suggests they also recorded temporal information, marking when events occurred and tracking calendrical data. The colors of strings might indicate what was being counted, the length and spacing of chords could carry meaning, and the overall structure of a quipu could represent complex relationships between different types of information. Some scholars believe quipus might have even encoded narrative information, though this remains controversial and difficult to verify since the knowledge of how to read them fully was largely lost after the Spanish conquest. What's clear is that the Inca used quipus to track time-related information such as labor obligations owed at particular times of year, agricultural cycles, and ceremonial calendars. Quipu keepers, called quipucamayarchs, were trained specialists who could create and read these devices, passing information across the empire. The quipu represents a completely different approach to recording information than writing, one based on three-dimensional structure, texture, and color rather than two-dimensional marks on a surface. That this system could encode both quantities and temporal information demonstrates that humans can develop sophisticated information storage and communication systems through many different modalities, and that our alphabetic writing is just one solution among many to the challenge of preserving and transmitting knowledge across space and time. The Antikythera mechanism predicted eclipses over 2,000 years ago. In 1901, divers searching for sponges off the Greek island of Antikythera discovered an ancient shipwreck. Among the artifacts they recovered was a corroded lump of bronze that, when examined, turned out to be one of the most astonishing archaeological finds ever made. The Antikythera mechanism, dating from around 100 BCE, is an intricate mechanical device containing dozens of precisely cut bronze gears. When researchers finally managed to reconstruct how it worked, they realized it was an astronomical calculator of remarkable sophistication. By turning a crank, a user could set the device to any date, and the mechanism would show the positions of the Sun, Moon, and probably the 5 planets known to the ancient Greeks. It could predict lunar and solar eclipses, accounting for the irregular motion of the Moon through its cycle. It tracked the timing of the Olympic Games. It incorporated knowledge of the Metonic cycle and other long-period astronomical patterns. The precision of the gear work, the complexity of the mechanisms, and the depth of astronomical knowledge required to design such a device are extraordinary for something created more than 2,000 years ago. Nothing comparable to the Antikythera mechanism appears again in the historical record for over a millennium. It represents a peak of ancient mechanical engineering and scientific knowledge that was subsequently lost. The mechanism reminds us that ancient peoples were capable of remarkable technological and intellectual achievements, that the development of science and technology hasn't followed a simple upward trajectory, and that knowledge can be lost as well as gained. It also demonstrates humanity's ancient fascination with tracking and predicting time, with understanding the cycles of the heavens and creating devices that capture those cycles in mechanical form. The Antikythera mechanism is a 2,000-year-old testament to the human drive to measure time, to predict the future, and to encode knowledge in lasting, material form. The doomsday clock symbolizes global catastrophe risk. In 1947, a group of atomic scientists, many of whom had worked on the Manhattan Project developing the first nuclear weapons, founded a magazine called the Bulletin of the Atomic Scientists. Concerned about the existential threat posed by nuclear weapons, they created a symbol to communicate to the public how close humanity was to self-destruction: the doomsday clock. The clock is not a prediction or a statistical model. It's a metaphor, a communication tool designed to focus attention on global catastrophic risks. Midnight represents catastrophe, the end of civilization, possibly the extinction of humanity. The clock's hands show how many minutes or seconds remain until midnight, with closer times indicating greater danger. The clock started at 7 minutes to midnight in 1947. Its position has changed 25 times since then, moved forward or backward by the Bulletin Science and Security Board based on their assessment of threats facing humanity. Initially focused solely on nuclear weapons, the clock now considers other catastrophic risks: climate change, biological weapons, disruptive technologies, and breakdowns in international institutions and norms that could lead to war or civilizational collapse. The doomsday clock has been criticized as unscientific, as fear-mongering, as oversimplification of complex risks. But it has also been remarkably successful as a piece of communication, a vivid metaphor that captures public attention and creates urgency around existential threats. When the clock moves closer to midnight, news outlets around the world report it. People who might not otherwise engage with complex technical discussions about nuclear arsenals or climate tipping points pay attention to whether humanity's metaphorical time is running out. The clock reminds us that time isn't just something we measure and organize. It's also something we run out of, individually and collectively, and that our choices determine how much time we have left. It reached 100 seconds to midnight in 2020 and 90 seconds in 2023. In January 2020, the Bulletin of the Atomic Scientists moved the doomsday clock to 100 seconds to midnight, the closest it had ever been to symbolic catastrophe. For the first time in the clock's history, the time was measured not in minutes but in seconds. The decision reflected multiple converging threats: the continued existence of approximately 13,000 nuclear weapons, several near misses and close calls between nuclear powers, the accelerating climate crisis with inadequate response, the destabilizing effects of cyber-enabled information warfare, and weakening international agreements and institutions designed to manage global risks. Then in January 2023, the clock moved even closer, 90 seconds to midnight, a new record. This adjustment came in response to Russia's invasion of Ukraine and the resulting increased nuclear risk, continued failures to address climate change at the necessary scale and speed, ongoing threats from biological weapons and pandemics after COVID-19, and the proliferation of disruptive technologies including artificial intelligence systems deployed without adequate safety measures or governance. Frameworks. These settings, measured in seconds, convey a message of extreme urgency. The experts maintaining the clock are saying that humanity is living in a moment of acute danger, that the decisions made in the coming years will determine whether we navigate these risks or succumb to them. Whether one agrees with the specific assessments or not, the doomsday clock serves as a reminder that time matters not just in the abstract but in the most concrete and urgent sense. We face challenges that cannot be deferred indefinitely, problems that compound if left unaddressed, tipping points beyond which recovery becomes impossible. The clock, with its hands hovering so close to midnight, asks us to consider what we're doing with our time, both individually and collectively, and whether we're using it wisely while we still have it, before the symbolic midnight strikes and time, at least for human civilization as we know it, runs out. Historical timelines distort intuition. Our minds struggle with the true scale of history. We imagine the past as a series of distinct periods, separated by clear boundaries, moving in orderly progression from ancient times through medieval ages to the modern era. But this mental organization, while useful, creates false impressions about what existed when and how long different periods actually lasted. We compress millennia into mental categories, imagining that ancient Egypt, ancient Greece, and ancient Rome were somehow close together in time because they all feel ancient to us. We forget that Cleopatra lived closer in time to the invention of the iPhone than to the building of the Great Pyramid. Our intuitive sense of historical time is distorted by several factors. We pay more attention to recent history, so the past few centuries feel longer and more detailed than the vast stretches of earlier time. We organize history around major civilizations and events we learned about in school, creating the impression that these represent all of human experience rather than small highlights selected from an immense tapestry. We also tend to imagine that technological progress happened faster than it actually did, that the modern world arrived suddenly rather than emerging gradually over centuries. The reality is that history is full of surprising overlaps and unexpected continuities. Institutions, technologies, and empires often persisted much longer than we imagine. Things we think of as ancient sometimes lasted well into what we consider the modern era. And things we imagine as having existed forever sometimes turn out to be remarkably recent inventions. Understanding these distortions doesn't just correct historical misconceptions. It changes how we think about time itself, revealing that our intuitive timeline is a construct, a story we tell ourselves, as shaped by psychology and culture as by actual chronology. Oxford University predates the Aztec and Inca empires. Oxford University, one of the world's oldest continuously operating educational institutions, began as an informal gathering of scholars in the English town of Oxford sometime in the 11th century. By 1096, teaching was definitely occurring there, though the university wouldn't receive formal recognition until later. The institution grew throughout the 12th and 13th centuries, establishing colleges, developing governance structures, and becoming a major center of learning in medieval Europe. Meanwhile, on the other side of the Atlantic Ocean, the civilizations that would become the Aztec and Inca empires didn't yet exist. The Aztec people began their rise to power in the Valley of Mexico in the 14th century, founding their capital Tenochtitlan in 1325. The Inca Empire began its major expansion even later, in the early 15th century. By the time these great American civilizations were at their height, Oxford had already been educating students for 3 centuries. It had weathered plagues, political upheavals, and religious reforms. It had produced scholars who transformed philosophy, science, and theology. When Spanish conquistadors encountered the Aztec and Inca empires in the early 16th century, ending both civilizations within a few decades, Oxford continued on. It adapted to the Reformation, to the scientific revolution, to the modern age, persisting while empires rose and fell. This juxtaposition challenges our mental categories. We think of Oxford as a venerable institution, certainly, but still somehow modern, part of the contemporary world of universities and academic research. The Aztecs and Incas feel ancient, lost civilizations known to us mainly through archaeology and fragmentary records. Yet Oxford is older, having existed before they began and continuing after they ended. It reminds us that continuity and change operate on different timescales for different cultures and institutions, and that what endures isn't always what seems most powerful in its moment. The Ming Dynasty outlasted modern U.S. history. The Ming Dynasty ruled China from 1368 to 1644, a span of 276 years. During this period, China was the world's most populous country and arguably its most advanced civilization. The Ming built the Forbidden City, extended the Great Wall to much of its current form, sponsored the voyages of Zhang He, whose treasure fleets explored the Indian Ocean, and presided over flourishing arts, literature, and ceramic production that gave us the term Ming vase. The Ming Dynasty saw emperors and empires rise and fall elsewhere in the world. It began during the 100 Years' War in Europe and lasted through the Renaissance, the Protestant Reformation, and well into what Europeans call the Age of Exploration. By contrast, the United States has existed in its current form since the ratification of the Constitution in 1788, a span of just over 235 years as of now. The Ming Dynasty lasted longer than the entire history of the United States as a constitutional republic. This comparison highlights how young many modern nations are compared to the historical spans of empires and dynasties. The nations that dominate our current world, that seem so permanent and established, are actually quite recent creations in historical terms. The United States, despite being one of the world's older continuous constitutional governments, hasn't yet matched the longevity of numerous past civilizations and ruling houses. China itself, of course, has a recorded history stretching back over 3,000 years, with dynasties rising and falling across millennia. The Ming was just one in a long succession, itself eventually replaced by the Qing dynasty, which lasted another 268 years until 1912. These vast temporal scales of Chinese civilization dwarf not just American history but the histories of most currently existing nations, reminding us that the modern map of countries is a very recent snapshot of human political organization, and that different ways of organizing society have persisted for far longer than most of today's governments have existed. The guillotine operated into the space age. The guillotine, the infamous execution device of the French Revolution, evokes images of the 18th century, of the Reign of Terror, of tumbrils carrying aristocrats through Paris streets to their deaths. It feels like an artifact of a distant, brutal past. Yet France continued using the guillotine for executions well into the 20th century. The last public guillotining in France occurred in 1939. The same year that Germany invaded Poland and World War II began, the same year that the first commercial television broadcasts occurred in the United States, the same year that Hewlett-Packard was founded and the jet engine was invented. France moved executions behind prison walls after that public spectacle drew massive crowds, but guillotine executions continued in private for decades more. The last person executed by guillotine in France was Hamida Jandoubi in 1977. By this time, the space age was well underway. Humans had walked on the Moon 8 years earlier. The Voyager spacecraft were preparing for launch to explore the outer solar system. Personal computers were beginning to appear. Star Wars had just been released in theaters. And in France, execution by guillotine continued, a revolutionary-era technology persisting into the modern world. France abolished the death penalty entirely in 1981, finally ending the guillotine's use. This unexpected persistence challenges our assumption that history moves in neat stages, that old technologies and practices disappear when we move into new eras. Instead, things overlap in surprising ways. The space age and the guillotine coexisted. The modern world emerged not through clean breaks with the past, but through gradual, uneven transitions where elements from different eras mingled together in unexpected combinations. The Beatles overlapped with the last woolly mammoths. This fact requires clarification, as it sounds impossible at first. The Beatles formed in 1960, and woolly mammoths are Ice Age creatures that went extinct thousands of years ago. Except they didn't all go extinct then. While mammoths vanished from continental areas around 10,000 years ago, small populations survived on remote islands for thousands of years longer. On Wrangel Island, a small landmass in the Arctic Ocean north of Siberia, a population of woolly mammoths persisted until approximately 1650 BCE, roughly 4,000 years ago. These island mammoths were isolated and had evolved smaller body sizes than their continental ancestors, but they were still recognizably woolly mammoths, the same species that had once ranged across Ice Age tundra alongside humans, cave lions, and other megafauna. When these last mammoths died out, the pyramids of Giza had already been standing for nearly 1,000 years. The ancient Sumerians and Akkadians were long gone. The Minoan civilization was flourishing on Crete. Writing, cities, complex civilizations had existed for over 2,000 years. The woolly mammoth, creature of the Ice Age, contemporary of Neanderthals and early modern humans, survived into what we would recognize as historical time, into the age of written records and established kingdoms. And then, thousands of years later, 4 young men from Liverpool formed a rock band. Obviously, the mammoths and the beetles didn't coexist in any meaningful sense. But this comparison highlights how much longer mammoths persisted than we typically imagine, how recently in geological and even historical terms the Ice Age megafauna disappeared, and how our intuitive timeline of prehistory versus history creates false boundaries, making us imagine wider gulfs in time than actually exist between events. The Colosseum finished closer to the iPhone era than the pyramids. The Roman Colosseum, that iconic symbol of ancient Rome, was completed around 80 CE during the reign of Emperor Titus. It stands as one of the most recognizable monuments from the ancient world, representing Roman engineering prowess and the brutal spectacles of gladiatorial combat. The Great Pyramid of Giza, the oldest and largest of the pyramids at the Giza complex, was built around 2560 BCE during the reign of Pharaoh Khufu. Let's do the math. From the completion of the Great Pyramid to the completion of the Colosseum is about 2,640 years. From the completion of the Colosseum to the release of the first iPhone in 2007 is about 1,927 years. The Colosseum is separated from us by less time than separates it from the pyramids. When Romans were building the Colosseum, the pyramids were already ancient monuments, over 2,600 years old. They were older to the Romans than the Romans are to us. This drives home a crucial point about the vast scale of ancient Egyptian civilization. Egypt's history spans such an enormous period that what we lump together as ancient Egypt actually encompasses millennia of change, multiple rises and falls, periods as different from each other as the Roman Empire is from our modern world. Cleopatra, who lived at the very end of ancient Egyptian civilization, was closer in time to the space missions and moon landings than to the building of the pyramids. The pyramids were as ancient to her as Julius Caesar is to us. Understanding these temporal relationships changes how we think about the ancient world. Egypt wasn't a brief flowering of civilization. It was a vast, enduring culture that persisted for longer than anything in Western history, and whose earliest monuments are separated from us by such gulfs of time that they seem to belong to a different world entirely, which in many ways they do. The 100 Years' War lasted 116 years. The 100 Years' War, the famous conflict between the kingdoms of England and France, didn't actually last 100 years. It lasted longer. The traditional dates given for the war are 1337 to 1453, a span of 116 years, though some historians argue about exactly when it began and ended. The name 100 Years' War wasn't used by people living through the conflict. It was applied by historians later as a convenient label for what was actually a series of campaigns, truces, and renewed hostilities spanning multiple generations. The war wasn't continuous fighting for 116 years. There were periods of intense military activity alternating with years or even decades of peace or low-level conflict. Truces were signed and broken. Entire generations lived and died while the conflict simmered, occasionally flaring into major campaigns. The war saw tremendous changes in military technology and tactics. It began in an era dominated by mounted knights and ended in an era where gunpowder weapons and professional armies were becoming important. Joan of Arc, one of the war's most famous figures, appeared near its very end, in the early 1430s, more than a century after the war began. The discrepancy between the name and the actual duration reminds us that historical periodization is often approximate, that events don't fit neatly into the categories we create for them. The 100 Years' War wasn't a discrete event with a clear beginning and end. It was a long, complex period of conflict with roots stretching back before 1337 and consequences extending beyond 1453, involving dynastic disputes, economic competition, and cultural antagonism that shaped England and France for centuries. Calling it the 100 Years' War is simpler than calling it the 116 Years' War, so the name stuck, even if it's not quite accurate. The shortest war in history lasted under an hour. At the opposite extreme from central-long conflicts, we have the Anglo-Zanzibar War, which holds the record as the shortest war in recorded history. It lasted between 38 and 45 minutes, depending on which historical sources you consult. The war occurred on August 27, 1896, between the United Kingdom and the Zanzibar Sultanate, a small nation on the east coast of Africa that was essentially a British protectorate. The conflict arose over succession to the Sultanate. When Sultan Hamad bin Thuwaini died, Khalid bin Bargash seized power, claiming the throne. Britain preferred a different candidate and demanded that Khalid step down. When he refused and barricaded himself in the palace with about 2,800 supporters and several artillery pieces, British warships in the harbour issued an ultimatum: abdicate by 9 a.m. or face attack. Khalid did not abdicate. At 9:02 a.m., British ships opened fire. They bombarded the palace, quickly overwhelming Zanzibar's defences. The palace was set on fire. Khalid's artillery was destroyed. By 9:40 a.m., the fighting was over. Khalid escaped to the German consulate and eventually went into exile. British forces suffered one wounded sailor. Zanzibar's casualties were estimated at around 500 killed or wounded. Britain installed their preferred sultan, and Zanzibar continued as a British protectorate for another 67 years until independence in 1963. The Anglo-Zanzibar War demonstrates that while some conflicts drag on for generations, others can be decided in minutes when there's an overwhelming disparity in military power. It's a curiosity of history, the briefest of wars, lasting less time than many meetings or meals, yet still involving hundreds of casualties and changing the political fate of a nation. The contrast between this 38-minute war and the 116-year 100 Years' War shows the enormous range of temporal scales on which human conflicts unfold. Annie Jump Cannon catalogued 225,000 stars by hand, now done by AI in seconds. In the early 20th century, at Harvard College Observatory, a group of women known as the Harvard Computers worked on classifying stars. Among them, Annie Jump Cannon became the most prolific. Over the course of her career, she personally classified approximately 225,000 stars, examining photographic plates through a magnifying glass and categorizing each star's spectrum by hand, recording her findings in ledgers. She developed the stellar classification system still used today, the sequence O, B, A, F, G, K, M, remembering through the mnemonic "Oh, be a fine girl, kiss me." Her work required extraordinary patience, attention to detail, and expertise. Each star had to be examined individually, its spectral characteristics noted, its position recorded. The task took decades of painstaking labor. Today, automated systems and artificial intelligence can classify stars by the thousands per second, analyzing spectroscopic data from digital surveys and applying machine learning algorithms trained on millions of examples. What took Annie Jump Cannon a career of dedicated work can now be accomplished in seconds by computers. This comparison isn't meant to diminish Cannon's achievement. Her work was foundational, establishing the classification framework and demonstrating the importance of systematic stellar surveys. The algorithms that now automate her work exist because of pioneers like her. But the comparison illustrates the astonishing acceleration of information processing enabled by computers. Tasks that once required human lifetimes of effort now happen faster than we can perceive. This acceleration changes what's possible in science, enabling surveys of billions of stars, analysis of vast datasets, discoveries that would be impossible if humans had to process every data point manually. It also raises questions about what role humans will play in a world where so many cognitive tasks can be automated, where the painstaking handwork of experts becomes something computers do as effortlessly as we breathe. Time compresses history into unexpected juxtapositions. All of these examples illustrate a common phenomenon. Our intuitive understanding of history compresses time in misleading ways. We imagine clear boundaries between eras that actually overlapped messily. We separate things that coexisted and group things that were separated by vast stretches of time. This compression happens for several reasons. Our brains aren't good at reasoning about very long timescales. 100 years, 1,000 years, 10,000 years all feel vaguely similar, all lumped into the category of a long time ago. We organize history around familiar touchstones, the civilizations and events we learned about, creating the impression that these represent all of history rather than scattered highlights from an immense continuum. We're also influenced by narrative convention. History is taught as a story with chapters and periods, and stories have clear beginnings and endings, neat transitions from one episode to the next. But real history doesn't work this way. Old things persist alongside new things. Technologies and institutions outlive their original contexts. Civilizations overlap in time even when they're separated by geography and never interact. The Renaissance began while the Ming dynasty was flourishing, while the Inca were expanding their empire, while the Ottoman Turks were conquering Constantinople. All these events happened simultaneously, but we learn about them separately, creating the false impression that they belong to different eras. Understanding these juxtapositions doesn't just correct misconceptions about when things happened. It changes how we understand causality and influence, how we think about what's ancient versus modern, what's beginning versus ending. It reveals that history is not a sequence of discrete periods but a vast, interconnected web of overlapping processes, some changing rapidly and others persisting for millennia, all unfolding simultaneously across the surface of a planet where time, however we measure and divide it, simply continues, carrying everything forward together into whatever futures await.